The detector trace on the monitor does not look like a star at first. It looks like a rhythm, a pattern of counts rising and falling as X-rays arrive from a point so small that no telescope can turn it into a surface. The source is not glowing like a normal star. It is flashing, rotating, dragging a magnetic field through space, and every pulse that reaches the instrument has crossed years, centuries, or thousands of years before becoming a number in a data file. A neutron star can hide inside that rhythm. There may be no bright disk to photograph, no wide surface to resolve, no gentle outline like a planet against a sun. There is only timing, energy, polarization, a coordinate on the sky, and the behavior of matter pushed so far past ordinary experience that the familiar language of rocks, gas, and flame begins to fail. The star itself might be only about the width of a large city, but it can hold more mass than the sun. Its gravity crushes atoms until electrons and protons are forced into a state dominated by neutrons. Its crust may be harder than steel by a margin that makes steel seem soft. Its magnetic field may be strong enough to shape radiation, tear particles from the surface, and in the most extreme cases, power eruptions that briefly outshine almost everything else in the high-energy sky. If objects like this are what bring you here, subscribing keeps the next long journey close. To approach a neutron star, it helps to begin with the kind of evidence that can actually reach Earth. A radio dish hears a repeating signal. An X-ray telescope records a pulse profile. A gamma-ray detector catches a flare so brief that it is almost over before the spacecraft can turn its attention toward the source. A gravitational wave detector records a tiny change in length as two dense remnants spiral together in another galaxy. None of these measurements is the star itself, but each one is a trace left by the same kind of object. The title sounds like it belongs to spectacle, because neutron stars and magnetars are often introduced through extremes, the strongest magnetic fields, the densest stable matter, the fastest spins, the most violent flares. But the more interesting story is not simply that they are extreme, it is that they are real, measurable, and still incomplete. They are not symbols of darkness. They are laboratories made by gravity, where physics is forced into a regime no experiment on Earth can fully reproduce. A normal star is a balance between collapse and pressure. Gravity pulls inward. Fusion in the core releases energy that pushes outward. For millions or billions of years, depending on the mass of the star, those forces negotiate with each other. The star shines because that negotiation is happening deep inside it, where hydrogen becomes helium, helium becomes heavier elements, and radiation slowly works its way toward the surface. For the most massive stars, that balance cannot last. The core burns through one fuel after another, each stage shorter than the last. Hydrogen burning may last millions of years. Helium burning is shorter. Carbon, neon, oxygen, and silicon burning arrive like the final chapters of a book being read faster and faster. By the time iron builds up in the core, fusion no longer gives the star an easy way to support itself. Iron is a turning point because fusing iron does not release energy in the way earlier fusion stages do. The core becomes heavy, hot, and unstable. Electrons are squeezed into protons. Neutrinos flood outward. Pressure fails. The inner core collapses in less than a second, and the outer layers of the star, still unaware that the center has changed, begin to fall after it. The collapse is not a slow dimming, it is a gravitational disaster unfolding inside a star that may have been shining for millions of years. Material falls inward at enormous speed. The core reaches nuclear density. It stiffens. A shock wave forms and tries to move outward through the infalling gas. Neutrinos carry away a huge amount of energy, and some of that energy helps revive the shock that will become a supernova. From outside, the event appears as the death of a star. From inside, it is also the birth of something new. The outer layers are thrown into space, carrying oxygen, silicon, calcium, iron, and other elements into the surrounding interstellar medium. The core that remains is no longer a normal star, no longer supported by fusion, and not yet, in many cases, a black hole. It is a neutron star, the exposed remnant of a stellar core compressed into a volume that would fit inside a metropolitan area. The first thing that becomes difficult is scale. A white dwarf may be roughly the size of Earth. A neutron star is much smaller than that, but much denser. The Moon is thousands of kilometers across. Earth is nearly 13,000 kilometers across. A neutron star may be 20 or 30 kilometers across, depending on its mass and the nature of matter in its interior. It is an entire stellar core folded down into a landscape that, on a map, would not look much larger than a city and its suburbs. The second thing that becomes difficult is density. Ordinary matter is mostly empty space because atoms are mostly empty space. In a neutron star, that emptiness is largely gone. The material is not solid in the everyday sense, and it is not a gas in the everyday sense. It is matter under pressure so intense that the structure of atoms has been erased. The density approaches the density of an atomic nucleus, not in a tiny particle, but across a star. A teaspoon comparison is often used because it gives the mind something to hold. It is not perfect, because no one can scoop neutron star matter and carry it away. Removed from the pressure that maintains it, the material would not remain in that form. But as a way of imagining density, it helps. A small volume from the interior would contain a mountain range worth of mass by human standards. Because mass has been packed into a region where atoms can no longer keep their usual shape. Gravity on the surface is equally hard to translate. A person could not stand there, and no spacecraft could land there in any ordinary sense. The gravitational field would flatten matter, accelerate falling material to fractions of the speed of light, and bend the path of light itself. If the surface emits radiation, some of that radiation can curve around the star before escaping, allowing distant observers to see more of the surface than simple geometry would suggest. This matters because neutron stars are not studied like nearby planets. No probe is approaching one. No camera is resolving a mountain or a horizon. Knowledge comes from light curves, spectra, timing residuals, glitches, bursts, gravitational waves, and models of dense matter tested against those signals. Every claim about a neutron star has to pass through layers of inference because the object is too small, too distant, and too physically extreme for direct inspection. The earliest neutron stars did not enter astronomy as neat theoretical objects on a classroom diagram. They appeared as strange signals. In the 1960s, radio astronomers were building instruments to study the sky at wavelengths invisible to human eyes. The data could look like pen marks, chart recordings, or later, digital traces. Hidden in that data were pulses so regular that they seemed at first to invite the wrong kind of explanation. Jocelyn Bell Burnell, then a graduate student, noticed a repeating radio signal in 1967. It was too precise to ignore. The source appeared at the same sidereal time, tied to the stars rather than to earthly interference. It was jokingly labeled with language that hinted at artificiality, but the explanation that survived was far stranger and more natural. A rotating neutron star could act like a lighthouse, sweeping a beam of radio emission across Earth each time it turned. Pulsars changed neutron stars from theoretical remnants into observable objects. A pulsar does not pulse because the whole star expands and contracts like a beating heart. It pulses because the beams of radiation are misaligned with the spin axis, and as the star rotates, those beams cross our line of sight. If Earth sits in the path, the telescope receives a burst of radio waves, X-rays, or gamma rays with each rotation. Some pulsars rotate slowly, once every few seconds. Others rotate hundreds of times per second. The fastest known millisecond pulsars have been spun up through long interactions with companion stars, pulling in material and angular momentum until the old neutron star turns with astonishing speed. The star is not large, but its surface, if imagined as a rotating shell. is moving at a significant fraction of the speed of light. This rapid rotation is a fossil of the collapse that made the star. A massive star may rotate modestly before it dies. When the core collapses, conservation of angular momentum spins it up, the way an ice skater spins faster when drawing in their arms, but on a scale where the arms are the core of a star falling inward by thousands of kilometers. The result can be a newborn neutron star rotating many times per second. Magnetic fields are also intensified during collapse. A star already has magnetic structure, but compression can concentrate the field into a much smaller volume. Rotation can amplify it further through dynamo processes in the newborn remnant. In many neutron stars, the magnetic field is already far beyond anything familiar. In magnetars, it becomes the defining feature, not merely a detail of the star, but a source of power. A magnetar is a neutron star whose magnetic field is so strong that its decay and rearrangement can supply the energy seen in X-rays and gamma rays. Ordinary pulsars are powered mainly by rotation, gradually losing spin energy as radiation and particles stream away. Magnetars can rotate comparatively slowly and still be bright in high-energy light, because the magnetic field itself is a reservoir of energy. This distinction is important because it changes how the object behaves. A rotation-powered pulsar is like a flywheel losing energy over time. The timing can be extremely stable, though not perfect. A magnetar is more restless. Its crust and magnetic field are tied together. Stresses build. The field twists. The crust may crack or shift. The magnetosphere can rearrange. A quiet source can suddenly produce a series of bursts, then fade again into a different state. The word crust can be misleading if it suggests something Earth-like. A neutron star crust is not rock. It is a layer of nuclei and electrons under pressure that increases with depth, eventually giving way to stranger arrangements of nuclear matter. Near the surface, there may be an atmosphere only centimeters thick, if one exists at all. Below that, nuclei are packed into a lattice, and deeper still, the nuclei may deform into shapes that scientists compare to sheets and tubes because there is no everyday vocabulary for the geometry of matter under these conditions. The interior is one of the major unsolved problems. It may contain superfluid neutrons, superconducting protons, and particles that rarely appear in ordinary matter. At the highest densities, some models allow more exotic phases, including hyperons or deconfined quarks. But the exact answer is not known. The pressure-density relation, called the equation of state, determines how large a neutron star can be for a given mass and how it behaves during a merger. The equation of state is not a decorative detail. It decides whether a neutron star with two solar masses can exist without collapsing. It shapes the gravitational waves produced when two neutron stars spiral together. It affects how X-rays from hotspots bend around the star. It determines whether matter is relatively stiff, holding the star larger, or softer, allowing gravity to compress it further. Astronomers cannot open a neutron star and examine the interior, so they look for indirect tests. A precisely measured mass rules out some models. A radius estimate rules out others. A merger waveform constrains how easily the star is deformed by its companion. Each measurement removes a few possibilities and leaves others standing. Progress comes not as a single revelation, but as a narrowing corridor through dense nuclear physics. One of the instruments built for this work is NICER, mounted on the International Space Station. It watches neutron stars in soft X-rays, recording the arrival times of individual photons with high precision. The goal is not to make a conventional photograph. The goal is to reconstruct how hotspots on a rotating neutron star appear as the star spins, and from that changing pulse shape. Infer mass, radius, and surface geometry. The method is subtle. A hotspot rotates into view, brightens, rotates away, and dims. But gravity bends the light, so the spot may remain partly visible when simple geometry says it should be hidden. The exact shape of the pulse depends on the star's compactness, on the spot locations, on the emission pattern, and on the viewing angle from Earth. Models are compared against data until certain combinations become more likely than others. This is one reason neutron stars feel both close and distant. They are close in the sense that the physics is written into measurable signals. They are distant in the sense that every measurement is folded through gravity, magnetic fields, plasma, detector response, and statistical uncertainty. The star is never simply shown. It is reconstructed. The Crab pulsar is one of the clearest examples of a neutron star still connected to the explosion that made it. In the year 1054, observers on Earth recorded a new star bright enough to be visible in daylight. Today, telescopes see the Crab Nebula as a glowing remnant, a tangled structure of filaments and high-energy particles. At its center sits a pulsar rotating about 30 times per second, feeding energy into the nebula around it. In optical images, the Crab Nebula can look like a delicate web. In X-rays, it becomes a more violent machine with rings, jets, and a compact central engine. The pulsar's wind of particles collides with surrounding material and magnetic fields, producing radiation across the spectrum. The remnant is not merely a cloud left behind by a dead star. It is being actively powered by the spinning neutron star at its center. A pulsar slows down as it loses rotational energy. The Crab is young enough that this slowing can be measured clearly. The period changes by tiny amounts, but over time, those tiny changes matter. The energy lost from rotation appears in the surrounding nebula and in high-energy emission. A neutron star may be small, but when it is young and rapidly spinning, it can influence a region of space far larger than itself. Some neutron stars reveal their interiors through glitches. A pulsar glitch is a sudden change in rotation rate, usually a small spin-up. The effect may come from interactions between the solid crust and superfluid components inside the star. For years, the pulsar slows gradually, then abruptly steps to a slightly faster rate before resuming its long decline. The signal is tiny, but it carries information from beneath the surface. The Vela pulsar is famous for such glitches. Its timing has been watched for decades, and each glitch becomes an opportunity to test ideas about superfluid vortices, crustal stresses, and the coupling between layers of the star. No telescope can see those layers. The evidence is in the clock. A neutron star is a natural chronometer, and when the clock stutters, the stutter becomes a probe. The magnetosphere around a neutron star is not empty. Rotation and magnetic fields pull charged particles from the surface or create them in cascades above the magnetic poles. Electric fields accelerate particles to extreme energies. Radiation emerges from regions that may be close to the surface or far out near the light cylinder, where co-rotation with the star would require motion at the speed of light. The beams we see from pulsars are shaped by this plasma environment. They are not searchlights bolted to a solid body. They are patterns of radiation generated by charged particles moving along magnetic field lines, radiating as they accelerate. Different wavelengths can come from different parts of the magnetosphere, which is why a pulsar's radio, X-ray, and gamma-ray pulses may not align perfectly. The idea of a lighthouse is useful, but only up to a point. A lighthouse beam comes from a lamp and mirror. A pulsar beam comes from a rotating relativistic plasma system locked to a magnetic field anchored in one of the densest objects known. The simplicity of the pulse hides the complexity of the engine. Magnetars take that complexity further. Their magnetic fields are so intense that the field becomes a major structural feature of the star's environment. The field can twist, store energy, and reconnect. It can support clouds of charged particles. It can change the way photons move through the vacuum around the star, because at such field strengths, even empty space must be treated with quantum caution. The magnetic field of a magnetar is often described by comparison. Earth's field is less than a Gauss at the surface. A refrigerator magnet is stronger than Earth, but still ordinary. A magnetar can reach around a quadrillion Gauss in common descriptions, though exact values vary by object and by how the field is inferred. The comparison is so large that it almost stops being helpful, but it does show why magnetars occupy a separate category among neutron stars. If a magnetar were close to Earth, its field would be catastrophic for technology and biology. But known magnetars are not close in that sense. They are scattered across the Milky Way and beyond, distant enough that their danger is not the point. The point is that their light reaches us after crossing interstellar space, carrying the signature of magnetic energy being released in one of the most extreme environments nature produces. A magnetar outburst can begin with little warning. The source may be faint or quiet in archival data, then suddenly become bright in X-rays. Gamma-ray monitors that watch large areas of the sky may trigger on a burst lasting a fraction of a second. Follow-up observations then search for a fading afterglow, a changed pulse profile, a different spin-down rate, or a dust-scattering ring created as X-rays pass through material between the magnetar and Earth. In the magnetar model, the crust and field are coupled. The magnetic field inside the star can evolve and push against the crust from below. The crust resists until stress exceeds its strength. A shift, fracture, or plastic deformation changes the external magnetic field, and energy is released into the magnetosphere. The result can be a short burst, a storm of bursts, or, in rare cases, a giant flare. A giant flare is not simply a bigger version of an ordinary flare. It is a rare release of magnetic energy that can be detected across vast distances. The initial spike may last less than a second, followed by a tail modulated by the rotation of the neutron star. That tail tells astronomers that the source is compact, rotating, and magnetically trapped. The star's spin writes itself into the fading high-energy light. On December 27, 2004, a giant flare from the magnetar Skiar 180620 became one of the brightest high-energy events ever recorded from beyond the solar system. Detectors were saturated. Earth's upper atmosphere was disturbed. Later analysis of data from NASA's Rossi X-ray Timing Explorer found oscillations interpreted as vibrations of the neutron star crust or magnetosphere. For a moment, a star thousands of light-years away rang in the data. That ringing is important because it suggests a way to study the star's structure. Just as seismology on Earth uses waves to infer what lies below the surface, magnetar oscillations may reveal properties of the crust and interior. The analogy is limited because a neutron star is not a planet, but the principle is similar. Motion inside an object leaves a pattern at the surface, and careful instruments can sometimes recover that pattern. The flare also showed how deeply high-energy astronomy depends on readiness. The event was not predicted. It appeared in instruments already watching the sky. Spacecraft built for gamma rays, X-rays, solar physics, and particle monitoring all became witnesses. A magnetar does not wait for a telescope schedule. It erupts, the photons arrive, and whatever instruments are operating at that moment become part of the record. The rarity of giant flares makes every candidate valuable. A burst seen from the direction of another galaxy may resemble a short gamma-ray burst, and distinguishing one from the other requires position, duration, spectrum, afterglow searches, and sometimes the absence of gravitational waves. A magnetar flare in a nearby star-forming galaxy can masquerade as something else until the evidence is assembled. In 2023, ESA's Integral Observatory detected a brief gamma-ray burst associated with the galaxy M82. Follow-up work found no ordinary afterglow in X-rays or visible light, strengthening the interpretation that it was a giant flare from a magnetar in that starburst galaxy. M82 forms stars rapidly, and massive stars are the ancestors of neutron stars, so it is a plausible environment for young magnetars. This is how a distant magnetar enters the archive. Not as an image of a surface, but as a short burst, a position on the sky, a lack of expected afterglow, a comparison with known giant flares. and a galaxy whose stellar population makes the interpretation reasonable. Astronomy often advances through presence and absence together. What is seen matters. What is not seen can matter almost as much. Another magnetar, SGR 1935 plus 2154, changed the discussion around fast radio bursts. Fast radio bursts are millisecond flashes of radio emission, most of them coming from far outside the Milky Way. For years, their origins were debated because they were brief, distant, and difficult to localize. Then, in April 2020, a magnetar in our own galaxy produced a radio burst associated with an X-ray burst. The event did not prove that every fast radio burst comes from a magnetar. The universe rarely gives one explanation for every member of a diverse class, but it did show that magnetars can produce Ferb-like signals. That mattered because it connected a mysterious extragalactic phenomenon to a known type of object, one already capable of sudden magnetic energy release. Radio telescopes and X-ray satellites saw different parts of the event. The radio pulse lasted milliseconds. The X-ray activity lasted longer. Timing the relationship between them became part of the physics. Did the radio emission come from high above the surface, from a magnetospheric disturbance, from a shock, or from some other process? Models remain under discussion, but the source was no longer purely hypothetical. It was a named magnetar in the Milky Way. This is one of the recurring patterns in neutron star astronomy. A mystery appears first as an unexplained signal. Then, a known object produces something similar nearby, or a new instrument measures a missing property, and the mystery changes shape. It does not vanish. It becomes more specific. Instead of asking what fast radio bursts are in general, researchers can ask which magnetar conditions produce radio bursts, why most bursts do not look the same, and whether other engines also contribute. Neutron stars also reveal themselves in binary systems. A neutron star with a companion can pull gas from that companion if the orbit is close enough. The gas does not fall straight down. It forms an accretion disk, heats to millions of degrees, and shines in X-rays. Matter spirals inward, guided by gravity and sometimes by magnetic fields, until it reaches the star's surface or is stopped and channeled toward magnetic poles. X-ray binaries are not just bright objects, they are laboratories for accretion physics, nuclear burning, magnetic fields, and strong gravity. Some produce X-ray bursts when material accumulates on the surface and ignites in thermonuclear flashes. Others show pulsations because the accretion flow is channeled onto magnetic poles. The changing brightness can trace orbital motion, disk instability, and the behavior of matter falling onto a surface rather than disappearing through an event horizon. That distinction separates neutron stars from black holes. Both can have accretion disks. Both can produce jets and high-energy radiation, but a neutron star has a surface. Material that reaches it releases energy there. A black hole has an event horizon, beyond which light cannot return. By comparing systems, astronomers can test how much observed behavior comes from the disk itself and how much depends on the nature of the central object. Some neutron stars orbit other neutron stars. These systems are rare, but they matter profoundly. Two dense remnants lose orbital energy through gravitational waves and slowly spiral together. For millions or billions of years, the orbit shrinks. Near the end, the frequency rises, the gravitational waves strengthen, and the final seconds become a signal that detectors like LIGO and Virgo can record. G11700817, detected in August 2017, was the first gravitational wave signal from a binary neutron star merger that was also observed in light. The gravitational waves arrived first in the data stream. A short gamma-ray burst followed. Telescopes around the world searched the error region and found a fading source in the galaxy NGC 4993. For the first time, the same cosmic event was studied through space-time ripples and electromagnetic radiation. The optical and infrared light from the event was a kilonova, powered by the radioactive decay of heavy elements formed in neutron-rich debris. This connected neutron star merges to the origin of elements such as gold and platinum. The connection had been proposed before, but GW 170817 made it observational. Matter from the collision was thrown into space, and as it cooled and decayed, it lit the surrounding universe with a changing spectrum. A neutron star merger is both an ending and a factory. The two stars may form a heavier neutron star for a brief time, collapse quickly into a black hole, or follow a more complicated path depending on their masses and the equation of state. The outcome of GW 170817 remains a subject of study. The data tell us much, but not everything. The remnant itself was hidden behind distance, debris, and the limits of existing detectors. The gravitational wave signal carried information about tidal deformability. As the neutron stars approached each other, each star's gravity distorted the other. A larger, softer star would deform differently than a smaller, more compact one. Those distortions left subtle traces in the waveform. From those traces, scientists extracted constraints on neutron star radii and dense matter, adding another piece to the same puzzle. Nicer studies through X-rays. The merger also changed the way astronomy thinks about messengers. Light is one messenger. Gravitational waves are another. Neutrinos, cosmic rays, and particles can also carry information in different contexts. Neutron stars sit at the crossing point of several messengers because they are compact enough to shake spacetime, hot and magnetized enough to shine in high-energy light, and rich enough in neutrons to forge heavy elements during collisions. No single observatory can capture the whole story. A radio telescope may time the pulsar for decades. An X-ray telescope may map hotspots. A gamma-ray detector may catch a flare. A gravitational wave interferometer may hear the final seconds of a merger. An optical telescope may watch the kilonova redden over days. Each instrument sees a different face of the same underlying physics. The human part of this story often happens in control rooms and archives. A scientist opens a data file from an old satellite. A pipeline flags a burst. A timing residual refuses to fit the model. A sky map goes out to observatories across the world. None of this resembles standing beside the object. It is more like listening through layers of machinery for a pattern that nature has almost buried. Neutron stars are sometimes called dead stars, but that phrase can hide how active they are. They no longer burn fuel through ordinary fusion. They are not alive in any biological or stellar main sequence sense. Yet their rotation, magnetic fields, residual heat, accretion, crustal stress, and mergers can produce some of the most dynamic behavior in astronomy. A young neutron star cools by emitting neutrinos and photons. Its surface may remain hot enough to shine in X-rays for thousands to millions of years, depending on its properties. Cooling curves can test the composition of the interior, because different particles and superfluid states allow heat to escape at different rates. Even a fading neutron star is a physics experiment in thermal evolution. Some isolated neutron stars are radio-quiet. Some shine mostly in X-rays. Some are central compact objects in supernova remnants, visible as small high-energy points near the centers of expanding debris. Some are rotating radio transients, detected only through occasional pulses. Some may be too faint or beamed away from Earth, present in the galaxy but invisible to our instruments. The population we know is therefore not the full population. Pulsars are easiest to detect when their beams cross Earth. Magnetars are easiest to notice when they burst or shine in X-rays. Accreting neutron stars reveal themselves in binaries. Quiet old neutron stars drifting through the galaxy may be almost impossible to find unless they pass through dense material or happen to emit in a detectable way. Selection effects matter. The sky catalog is shaped not only by what exists, but by what telescopes can see, what wavelengths they observe, how long they watch, and what algorithms are designed to find. A neutron star with a beam pointed elsewhere may never be cataloged as a pulsar from Earth. A magnetar between outbursts may look like a faint X-ray source or not be recognized at all. This does not make the science weak. It makes the caution part of the science. Astronomers estimate birth rates by combining observations with models. They compare supernova rates, pulsar populations, magnetar lifetimes, and the number of remnants visible in X-rays. The result is not a perfect census, but a structured attempt to infer the unseen from the seen. The Milky Way likely contains many more neutron stars than the ones catalogued. Massive stars have been dying here for billions of years. Some remnants have become black holes. Some white dwarfs have followed different paths. But many cores must have ended as neutron stars, kicked into new orbits by asymmetric supernova explosions, moving through the galaxy as compact relics of stars that no longer exist. Those kicks can be strong. If a supernova explosion is not perfectly symmetric, the newborn neutron star can be launched at hundreds of kilometers per second. Some pulsars move rapidly across the sky, trailing bow shocks as their winds collide with interstellar gas. Proper motion measurements show that these objects are not fixed jewels in the background. They are bodies moving through the galaxy, carrying their violent birth histories with them. A neutron star born inside a supernova remnant may eventually outrun the visible debris. The remnant expands and fades. The pulsar continues on its path. Millions of years later, the connection may be hard to reconstruct. The parent star is gone. The explosion has dissolved into the interstellar medium. The neutron star remains, a dense core traveling through the thin gas between stars. Because neutron stars are small, their surfaces are extreme in ways that depend on details. The outermost layer may contain hydrogen, helium, carbon, or heavier elements, depending on fallback from the supernova, accretion from a companion, and nuclear burning. That thin atmosphere shapes the X-ray spectrum. A small change in composition can change how temperature and radius are inferred. Fallback material can also affect a young neutron star. After the supernova, some ejected gas may fail to escape and fall back toward the remnant. It may form a disk, bury magnetic fields, or alter the early spin evolution. In some models, fallback helps explain why certain young neutron stars have weak apparent magnetic fields. The details are still uncertain because the first years after a supernova are difficult to observe. Supernova remnants provide context. In X-ray images, shock-heated gas glows in colors assigned to different energies. Optical filaments trace cooler material. Radio maps show synchrotron emission from energetic electrons spiraling around magnetic fields. At the center, a neutron star may appear as a point source, a pulsar wind nebula, or nothing obvious at all. The absence can be as puzzling as the detection. Cassiopeia A is one such remnant with a compact object near its center. The supernova light likely reached Earth in the 17th century, though historical records are uncertain. Today, the remnant is one of the most studied objects in high-energy astronomy. Chandra and other telescopes have watched its expanding debris, its elemental distribution, and the compact central source that may be a young neutron star. Objects like Cassiopeia A remind us that a supernova is not a clean sphere. The explosion dredges up layers from the star, mixes elements, launches jets and clumps, and leaves asymmetries behind. Those asymmetries can influence the kick of the neutron star and the shape of the remnant. The birth of a neutron star is not a simple collapse in isolation. It is embedded in the final violence of a massive star. The matter inside a neutron star is more compressed than any stable matter known elsewhere. But there is a limit. If the remnant is too massive, no pressure can support it against gravity, and it collapses into a black hole. The maximum mass depends on the equation of state. Observed neutron stars with masses around 2 solar masses rule out models that are too soft, because those models would collapse before reaching such masses. At the other end, a neutron star must have enough mass to be stable as a neutron star rather than a white dwarf-like object. Nature makes them through collapse, mergers, and perhaps other channels. But not every compact mass becomes a neutron star. The boundaries between white dwarfs, neutron stars, and black holes are written in the relationship between gravity, quantum pressure, nuclear forces, and general relativity. General relativity is not optional near a neutron star. Gravity is strong enough that Newtonian intuition becomes incomplete. Time runs differently near the surface compared with far away. Light is redshifted as it climbs out of the gravitational well. The star's compactness changes the appearance of hotspots. During mergers, space-time itself carries energy outward as gravitational waves. The magnetic field adds another layer. In ordinary conditions, light travels through vacuum in straightforward ways. Around a magnetar, quantum electrodynamics predicts effects such as vacuum birefringence, where the magnetic field changes how different polarizations of light propagate. Observing such effects is difficult, but polarization measurements from high-energy sources are beginning to make this kind of physics more accessible. X-ray polarization is especially valuable because it can reveal geometry. Brightness tells us how many photons arrive. Spectrum tells us their energies. Timing tells us when they arrive. Polarization adds information about the direction of the electric field in the light, which can trace magnetic fields and scattering environments. For neutron stars and magnetars, that extra dimension may help separate competing models. The surface of a magnetar may not be uniformly hot. Magnetic fields channel heat, producing hotspots or warmer regions near magnetic poles. During outbursts, parts of the crust may heat and then cool over months or years. X-ray monitoring can follow that cooling, revealing how energy deposited in the crust diffuses outward. A light curve becomes a thermometer, pressed against matter no laboratory can make. Some magnetars show persistent X-ray emission that changes over time. The spectrum may harden before an outburst or soften afterward. The pulse profile may simplify or become more complex. The spin-down rate may change because the magnetosphere has been twisted, altering the torque on the star. These are small clues, but together they describe a magnetic system evolving around a compact object. The term soft gamma repeater came before the magnetar explanation was fully accepted. These sources emitted repeated bursts of relatively soft gamma rays compared with classical gamma ray bursts. Another class, anomalous X-ray pulsars, seemed strange because their X-ray brightness was too high to be powered by rotation alone. Over time, both classes came to be understood as manifestations of magnetars. This is a useful reminder that astronomical categories often begin observationally. Scientists name what the instruments show. Later, as theory improves and more wavelengths are added, separate categories may merge into one physical family. A soft gamma repeater and an anomalous X-ray pulsar were once defined by different observational behavior. The magnetar model gave them a shared engine. Even now, the boundaries are not perfectly clean. Some ordinary radio pulsars have high magnetic fields. Some magnetars emit radio pulses during certain phases. Some neutron stars behave in ways that blur simple labels. The family tree is not a set of separate boxes. It is a landscape of magnetic field strength, age, rotation, temperature, environment, and history. A newborn magnetar may spin rapidly and carry an enormous magnetic field. Such an object has been proposed as the engine behind some superluminous supernovae and long-lived high-energy transients. In this model, rotational energy from the newborn magnetar is injected into the expanding debris, making the explosion brighter than radioactive nickel alone could explain. The idea is powerful, but each event has to be judged by its light curve and spectrum. Some supernovae may indeed be powered by magnetar engines, while others may involve interaction with circumstellar material, pair instability processes, or black hole accretion. Astronomy often offers multiple plausible engines for one bright event. The challenge is to identify which mechanism is actually operating, and sometimes the evidence is incomplete. A magnetar is not a universal explanation. It is one physical possibility among several. The connection between massive stars and neutron stars also depends on the life of the star before collapse. Mass loss, metallicity, rotation, binary interaction, and magnetic fields can all change the final core. Many massive stars live with companions, exchanging material or merging before they die. The compact object that emerges is shaped by that earlier history, much of which may be hidden by the time the supernova is observed. Binary evolution is especially important for double neutron star systems. To make two neutron stars in a tight orbit, two massive stars must both survive complex episodes of mass transfer and supernova explosions without the system being disrupted. The first star dies, leaves a neutron star, and may later accrete from the companion. The second star dies, giving the system another kick. If the binary remains bound, gravitational waves begin the long countdown to merger. The double pulsar system J07373039 is a rare case where both neutron stars have been observed as pulsars. It provides a precise laboratory for general relativity and binary evolution. The orbit shrinks as energy is lost to gravitational waves, just as theory predicts. Systems like this show that neutron-star mergers are not merely possible. They are the natural future of some binaries already visible in the Milky Way. Long before LIGO detected GW170817, the Hulse-Taylor binary pulsar provided indirect evidence for gravitational waves. Its orbit decayed at the rate predicted by general relativity. The system did not merge within human observing time, but its timing showed that orbital energy was leaving in the form of gravitational radiation. Decades later, interferometers measured such waves directly from compact object mergers. The path from a radio pulse to a gravitational wave chirp spans half a century of instruments: a chart recorder, a radio telescope, an atomic clock, a laser interferometer, an X-ray detector on the space station, and a gamma-ray monitor all belong to the same broad effort. They translate invisible physics into records that can be compared, challenged, and revised. Neutron stars also shape their surroundings through pulsar winds. A rapidly spinning neutron star drives a wind of relativistic particles into the space around it. When that wind hits slower material, it forms a termination shock, producing synchrotron radiation. In images, the result can be a pulsar wind nebula with rings, jets, and moving knots that change over time. These nebulae show that a neutron star can act like an engine long after the supernova. The Crab Nebula continues to shine because the central pulsar keeps injecting energy. Other pulsar wind nebulae, sometimes called Pleiadians, mark young energetic neutron stars embedded in remnants. Their shapes depend on the pulsar's motion, the surrounding gas, and the structure of the magnetic field. A fast-moving pulsar can create a bow shock. In optical or X-ray images, the bow shock may appear as a curved structure ahead of the star, like water pushed aside by a moving boat. Behind it, a trail of particles can extend for light years. The neutron star itself remains tiny, but its motion through interstellar gas turns it into a visible sculptor of the medium. Older neutron stars are often less dramatic. Their spin slows. Their magnetic fields may decay or become less active. Their thermal emission fades. Unless they accrete from a companion or beam radiation toward Earth, they can disappear from practical detectability. The galaxy may be filled with such remnants, moving quietly through the disk, known only through population models and the remnants of stellar evolution. The silence of old neutron stars is not empty. It is an observational silence, produced by distance, faintness, and geometry. A beam pointed away from Earth is not absent. A cold surface too faint for present instruments is not gone. This distinction matters in astronomy, where the universe is never simply the catalog. It is the catalog plus everything the catalog cannot yet reveal. When researchers model neutron star populations, they must account for beaming fractions, luminosity evolution, survey sensitivity, interstellar scattering, and the distribution of birth velocities. Radio waves from distant pulsars can be dispersed by free electrons between stars, delaying lower frequencies more than higher ones. That dispersion can be measured, and it gives clues about the interstellar medium as well as the pulsar. Pulsar timing arrays use millisecond pulsars as a galaxy-sized gravitational wave detector. The idea is simple in outline and difficult in practice. If low-frequency gravitational waves pass through the galaxy, they should slightly alter the arrival times of pulses from many stable millisecond pulsars in a correlated pattern. The pulsars become clocks distributed across the sky, and spacetime itself becomes the thing being monitored. These timing arrays are most sensitive to gravitational waves from supermassive black hole binaries, not ordinary neutron star mergers. But the method shows how neutron stars can be used as instruments. Their regular pulses, born from compact rotation and magnetic beaming, become tools for studying phenomena much larger than themselves. A dead stellar core becomes part of a galactic observatory. The precision is extraordinary. For the best millisecond pulsars, arrival times can be predicted with errors measured in microseconds or less over long spans, after accounting for orbital motion, interstellar effects, and the motion of Earth. Such stability makes them useful for tests of gravity, searches for planets around pulsars, and studies of the interstellar medium. Planets around pulsars were among the first exoplanets ever confirmed. That fact is easy to forget, because pulsar planets are not the kind of worlds usually imagined when exoplanets are discussed. They orbit stellar remnants, not sun-like stars. Their formation may involve fallback disks or second-generation material. The first confirmed exoplanet system was found not through starlight dimming, but through tiny changes in pulsar timing. Those worlds show that even after a supernova, planetary material can exist in unexpected arrangements. It does not mean such systems are common or gentle. The environment around a pulsar is harsh, filled with radiation and particle winds. But their discovery widened the idea of where planets might be found and demonstrated the power of timing as a detection method. Neutron stars also matter for nuclear physics on Earth. Laboratories can collide heavy ions and probe nuclear matter for fleeting moments, but they cannot hold a solar mass of neutron-rich material under its own gravity. Astronomers therefore provide constraints that nuclear physicists cannot obtain directly. A radius measured by X-ray timing, a mass measured by radio timing, and a tidal deformability measured by gravitational waves all feed back into the physics of nuclei. The collaboration between astronomy and nuclear physics is not optional for this subject. To understand a neutron star, one must understand gravity, relativity, quantum mechanics, plasma physics, magnetic fields, and nuclear interactions. The object forces disciplines together. It is one star, but the explanation cannot be contained inside one branch of physics. The limits of the explanation are just as important. When a scientist says the core may contain exotic matter, that is not a license to invent anything. It means certain models allow specific particles or phases under specific pressures. Those models must still support observed masses, fit radius constraints, and behave consistently during mergers. The unknown is bounded by evidence. This bounded uncertainty gives neutron stars their particular kind of mystery. They are not mysterious because nothing is known. They are mysterious because much is known, and the remaining unknowns are precise. We know enough to ask hard questions. What is the maximum mass? How stiff is dense matter? How are magnetar fields generated and maintained? Why do some magnetars emit radio bursts while others do not? What happens in the first second after two neutron stars merge? The first second after a merger is especially difficult. The gravitational wave signal is clearest during the inspiral, before contact. After the collision, the frequencies rise into ranges where current detectors are less sensitive. The remnant may be a hypermassive neutron star, a supermassive neutron star, or a black hole. It may survive for milliseconds, seconds, or longer. The electromagnetic emission gives clues, but the central engine is hidden by debris. Future detectors may hear the post-merger signal more clearly. If they do, The oscillations of the remnant could reveal the equation of state in a new way. Just as magnetar flares may let researchers listen to crustal vibrations, neutron star mergers may let them listen to the ringing of a newly formed compact object. The same theme returns. When the object cannot be seen directly, its vibrations become evidence. The kilonova debris from a merger expands rapidly and changes color as different elements shape the opacity. Lanthanides and other heavy elements can block blue light and reprocess energy into red and infrared wavelengths. This is why infrared telescopes are crucial for following such events. The color evolution is not merely beautiful. It is chemistry and nuclear physics written into the fading light. Heavy elements formed by rapid neutron capture require environments rich in free neutrons. Neutron star mergers provide such environments naturally. Material ejected during the collision can undergo our process nucleosynthesis, building nuclei heavier than iron. Some of those nuclei are unstable and decay, heating the debris and powering the kilonova. The gold in a ring may have a history connected to events like this, though not necessarily one specific event we can identify. Supernovae also make heavy elements, but the R process contribution from neutron star mergers has become a major part of the modern picture. The balance between different sites remains an active field. The early universe already contained some heavy elements, so rates, delay times, and yields matter. Again, the answer is not a simple slogan. It is a comparison between observations, simulations, and chemical evolution across galaxies. The simulations are demanding. They must include general relativity, nuclear physics, neutrino transport, magnetic fields, and turbulent fluid motion. A merger unfolds in milliseconds, but the debris can glow for days and affect galactic chemistry for billions of years. Models have to connect those scales, from a remnant smaller than a city to the enrichment of stars that may form long afterward. The same scale jump occurs in ordinary supernova remnants. A neutron star forms in less than a second, but its birth explosion can seed a nebula that expands for tens of thousands of years. The heavy elements drift into molecular clouds. New stars form. Planets condense. Meteorites preserve isotopic traces of earlier stellar deaths. Neutron stars are compact, but their consequences are not. A magnetar flare, by contrast, may be over almost instantly, yet its photons can affect detectors across the solar system and leave afterglows that radio telescopes follow for weeks. The timescale of release and the timescale of observation differ. A tenth of a second at the source becomes months of analysis, years of papers, and decades of theory refinement. This is why high-energy astrophysics values archives. A burst may be noticed after the fact, because a later discovery changes what researchers look for. Old data can contain unrecognized magnetar activity, unnoticed pulsations, or pre-outburst behavior. The telescope has already watched the sky. The question is whether anyone has asked the right question of its records. The reference frame of the star also matters. A pulsar rotating in 1 second may seem slow compared with a millisecond pulsar, but for a sphere 20 kilometers across, it is still extraordinary. A magnetar spinning every few seconds may be losing rotational energy quickly because its magnetic field applies a strong braking torque. The period alone does not tell the whole story. Period derivative, magnetic inference, luminosity, and spectrum must be read together. The standard magnetic field estimate for a pulsar comes from its spin period and spin-down rate under simplifying assumptions. It is useful, but it is not a direct measurement of every part of the magnetic field. A magnetar may have strong internal or multipolar fields not fully captured by the dipole estimate. Some low-field magnetars have shown magnetar-like behavior despite modest inferred dipole fields, suggesting hidden magnetic complexity. This hidden complexity is one reason magnetars remain difficult. The external dipole field controls some timing behavior, but the internal field may store much of the energy. The crust feels stresses from field components that are not easily visible from far away. A flare may therefore reveal energy that timing alone did not predict. The word magnetar can make the field sound static, like a permanent bar magnet. It is better to imagine a stressed magnetic structure embedded in and around a dense star, evolving through the motion of charged particles, crustal yielding, and gradual field decay. The field is not an accessory, it is a dynamic system tied to the star's thermal and mechanical evolution. Around a magnetar, the magnetosphere may be twisted. A twisted magnetosphere carries currents, and those currents can scatter X-rays from the surface, changing the observed spectrum. As the twist relaxes, the spectrum and pulse profile may change. This gives researchers a way to connect observed outbursts with magnetic geometry, though the models are complex and not always unique. Short magnetar bursts often last fractions of a second. They can come in storms, with dozens or hundreds of bursts during active episodes. The energy distribution, waiting times, and spectra are compared with models of crustal failure and magnetic reconnection. Some patterns resemble earthquakes in a statistical sense, but the underlying medium is a neutron star crust threaded by magnetic field, not terrestrial rock. A starquake on a magnetar is not a simple crack across a rocky surface. The crust may deform plastically, fracture locally, or trigger a magnetospheric instability. The exact process is still debated. The word starquake is useful because it conveys sudden stress release, but the physical details belong to dense nuclear matter and extreme magnetic fields. When such a burst reaches Earth, it is translated into counts in detectors. A gamma-ray instrument records energy deposits. An X-ray telescope records photons. A radio telescope may search for a pulse before or after the burst. Each instrument has dead time, sensitivity limits, background noise, and calibration issues. The event in the sky becomes a technical problem on the ground. This technical layer is part of the story because it keeps the mystery honest. Magnetars are not understood by awe alone. They are understood through instrument response matrices, timing corrections, sky localization, spectral fits, and repeated checks against alternative explanations. The emotional force of the object is real, but the evidence is mechanical, mathematical, and patient. Consider the first pulse from a newly discovered pulsar. It arrives as a small increase in signal. Then another at the same interval. The human mind notices rhythm quickly, but astronomy demands more. Is it local interference? Is it a satellite? Is it a known source? Does the timing repeat with the sky? Does dispersion indicate passage through interstellar electrons? Only after those questions does the rhythm become a star. Dispersion is one of the signatures that a radio pulse has crossed space. Lower radio frequencies arrive slightly later than higher frequencies, because free electrons in the interstellar medium slow them by different amounts. Measuring this delay gives a dispersion measure, a clue to distance and to the electron content along the line of sight. The space between stars becomes part of the signal. Scattering can smear a pulse, especially near the plane of the Milky Way, where ionized gas is denser. A sharp pulse may arrive with a tail. This affects how pulsars and fast radio bursts are detected. The path through the galaxy is not a clean vacuum for radio astronomy. It is a medium that alters the message, and those alterations must be modeled. For X-rays and gamma rays, interstellar gas absorbs some energies more than others. Dust can scatter X-rays into expanding rings after a burst, creating a delayed echo that maps material along the line of sight. Magnetar bursts have produced such rings, allowing astronomers to estimate distances and study intervening dust clouds. Again, the space between the star and Earth becomes an instrument. Distance is one of the hardest practical quantities. A pulsar's dispersion measure gives an estimate, but it depends on models of the galaxy's electron distribution. Parallax can measure distances for some nearby pulsars, using Earth's orbit as a baseline. Associations with supernova remnants or star clusters can help, but they can also be uncertain. Without distance, luminosity and energy become harder to pin down. This is why magnetar flare energies often carry caveats. If the distance is revised, the inferred energy changes. If the emission is not isotropic, the total energy may differ from what a simple spherical assumption gives. Astronomers often quote isotropic equivalent values because they are easy to compare, but the real geometry may be more complicated. Geometry shapes almost everything. The angle between spin axis and magnetic axis affects pulse profiles. The observer's line of sight decides whether beams are visible. The orientation of a merger affects the brightness of a kilonova and gamma-ray burst. A neutron star can be the same object physically and appear very different depending on how it is viewed. The star's age also changes its appearance. A young neutron star may be hot, rapidly spinning, and embedded in a remnant. A middle-aged pulsar may still beam radio waves but have a fading thermal surface. An old neutron star may be cold and slow unless revived by accretion. A recycled millisecond pulsar may be ancient but spin rapidly because a companion fed it angular momentum. Recycling is one of the more elegant transformations. A neutron star that has slowed over time enters a binary phase where gas from a companion spirals toward it. The accreting material carries angular momentum. Over millions of years, the star spins up. When accretion ends, the neutron star may emerge as a millisecond pulsar, rotating faster and more stably than many younger pulsars. Millisecond pulsars are common in globular clusters, where dense stellar environments encourage binary interactions. A globular cluster may contain many old stars. Yet its neutron stars can be active because encounters and mass transfer have altered their histories. The cluster becomes a crowded gravitational environment where compact remnants exchange partners, form binaries, and sometimes collide or merge. Globular clusters also show that neutron star history is not only about individual stellar evolution. Environment matters. A neutron star born in isolation follows one path. A neutron star in a binary follows another. A neutron star in a dense cluster may be dynamically exchanged into a new system. The same kind of object can have many biographies. Some neutron stars accrete matter until they approach limits that are still being studied. If enough mass accumulates, collapse to a black hole may occur. In other systems, accretion spins the star so fast that gravitational waves or magnetic torques may help limit further spin-up. The fastest observed spins are extremely rapid, but still below the theoretical breakup rates for many equations of state. Breakup is the point where rotation would overcome gravity at the equator and the star could not hold itself together. The exact limit depends on mass, radius, and interior physics. Observed spin rates therefore provide another constraint, though not yet as tight as mass and radius measurements. The absence of sub-millisecond pulsars may reflect physics, formation history, observational bias, or a combination. A neutron star's magnetic field can also evolve through accretion. Material falling onto the surface may bury the magnetic field, reducing the external dipole strength. Over time, the field may re-emerge. This process is one proposed ingredient in the evolution from ordinary pulsars to recycled millisecond pulsars. The details depend on accretion rate, total accreted mass, crust conductivity, and time. The crust itself is only a small fraction of the star by mass, but it matters disproportionately for observed behavior. It anchors magnetic fields, supports elastic stresses, participates in glitches, conducts heat, and responds to outbursts. Beneath it, the core contains most of the mass, but the crust is the layer through which many interior processes become visible. Neutron star mountains are another strange concept. Because gravity is so strong, the largest sustainable surface irregularities are tiny compared with planetary mountains. Yet even small asymmetries on a rapidly rotating neutron star could emit continuous gravitational waves if they are stable and large enough. Detectors search for such signals from known pulsars, turning surface shape into a possible source of space-time ripples. So far, continuous gravitational waves from a rotating neutron star have not been conclusively detected. Upper limits still matter because they constrain how lumpy these stars can be and how much energy they lose through gravitational radiation. Non-detections are not failures in the simple sense. They are measurements of what is not happening above a given level. The search for continuous waves is different from the search for mergers. A merger is brief and loud. A rotating asymmetric neutron star would be steady and faint, requiring long integration times and careful removal of detector noise. The signal would be like a persistent tone, hidden under the mechanical and environmental noise of the instrument. Instrument noise has its own geography. LIGO's mirrors hang in vacuum, isolated from seismic motion, but trucks, weather, ocean waves, thermal fluctuations, and quantum noise all matter. Radio telescopes deal with human interference, satellites, and ionospheric effects. X-ray telescopes deal with particle backgrounds and detector calibration. Every messenger arrives through a human-built system with its own imperfections. The remarkable thing is not that the measurements are imperfect. It is that they work at all. A neutron star thousands of light-years away can announce its spin through a radio pulse. A merger over 100 million light-years away can stretch and squeeze Earth by less than a proton's width relative to detector scale. A magnetar flare in another galaxy can register as a brief spike in gamma rays. These scales are easy to state and hard to feel. Light from the Crab Nebula has been traveling for about 6,500 years. Light from M82 takes about 12 million years. Gravitational waves from GW 170817 crossed roughly 130 million light-years before moving through Earth. The objects are small, but the distances are galactic and extragalactic. Looking at a neutron star is often looking backward. A flare that reaches a detector today may have occurred before human cities existed, depending on the distance. A merger observed in another galaxy happened when dinosaurs were long gone, but humans had not yet evolved. The signal is current to us only because light and gravitational waves have finite speed. Astronomy is always a study of delayed arrivals. This delay does not make the events less real. It makes the universe layered in time. A gamma-ray photon from a magnetar crosses dust clouds, spiral arms, intergalactic space, the heliosphere, and finally the detector material of a spacecraft. By the time it is counted, the source may have changed completely. The record is both a measurement and a preserved slice of the past. A telescope image of a supernova remnant is also a layered object. Some filaments show material ejected in the explosion. Some emission comes from shock waves heating gas. Some high-energy structures are powered by the central neutron star. The colors in the image may be assigned to wavelengths human eyes cannot see. The beauty is processed, but the physics is not invented. Processed color is often misunderstood. X-ray images are not what the eye would see through a window in space. They are translations of energy into visible colors so that structure can be studied. Blue may represent higher energy X-rays, red lower energy emission, green something between, depending on the image. The colors are choices, but the photons are real. For neutron stars, such translations are essential. Human eyes cannot see radio pulses, X-rays, gamma rays, or gravitational waves. The most important evidence arrives outside ordinary sight. The universe has to be converted into plots, maps, spectra, and waveforms before the mind can approach it. A neutron star is therefore both a physical object and a pattern of representations. The same object can look different in every wavelength. In radio, it may be a pulse. In X-rays, a hotspot or nebula. In gamma rays, sharp high-energy peaks. In optical light, perhaps nothing or a faint counterpart. In gravitational waves, only a merger or perhaps a future continuous signal. The star is one object, but observation divides it into channels. This division can create false simplicity. A catalog may list a period derivative, a magnetic field estimate, a distance, and an X-ray luminosity. The numbers look stable, but behind them are assumptions, uncertainties, and histories of observation. A neutron star is not exhausted by its catalog entry. The entry is a doorway into the evidence. The most extreme magnetars known are young by cosmic standards. Their intense magnetic fields decay over thousands to tens of thousands of years, heating the star and powering activity. Over longer times, they may become quieter, perhaps blending into other neutron star populations. The active magnetar phase may be brief compared with the age of the galaxy, which helps explain why known magnetars are relatively few. Their scarcity also makes each one important. A new magnetar discovery can test whether activity correlates with age, environment, field strength, or association with star-forming regions. A magnetar near the center of the Milky Way, for example, probes both extreme magnetic behavior and the environment around the central black hole. A magnetar in a star cluster can link compact remnants to recent massive star formation. The galactic center magnetar SGR J1745-2900 lies close in projection to Sagittarius A, the Milky Way's central supermassive black hole. Its radio pulses have been used to study the magnetized plasma near the galactic center. The source itself is a magnetar, but its location turns it into a probe of a much larger environment. Again, the neutron star becomes an instrument. A magnetar near a black hole also shows how different extremes coexist in one galaxy. A supermassive black hole contains millions of solar masses behind an event horizon. A magnetar contains a little more than the Sun's mass in a city-sized sphere with a surface. Both are compact, relativistic objects. Both shape nearby matter. But one is defined by an absence of surface, the other by the presence of one. That surface makes neutron stars uniquely violent in some contexts. Accreting matter can strike it and release energy directly. Thermonuclear burning can ignite on it. Magnetic stresses can heat or crack the crust. Hotspots can rotate in and out of view. A black hole can be more massive and more gravitationally extreme, but a neutron star's surface gives it behaviors that black holes cannot have. The surface is also where the magnetic poles become visible. Charged particles guided by field lines can bombard polar regions, heating them. These hotspots produce X-rays. Their shape may be circular, crescent-like, or more complex depending on field geometry. NICER's pulse profile modeling has shown that simple two-pole pictures do not always match the data, suggesting more complicated magnetic maps. Complex magnetic maps are expected if the crust and field have evolved through birth, cooling, Hall drift, and ohmic decay. The external dipole may be only the largest scale component. Smaller scale fields near the surface can produce hotspots that are offset, elongated, or asymmetric. When those spots rotate, their light curves become clues to hidden geometry. A pulsar's radio beam also has structure. Single pulses can vary. Some pulsars null, turning off temporarily. Some switch modes, changing pulse shape and spin-down behavior. The average pulse profile may look stable, but individual rotations can be messy. The magnetosphere is not a rigid lighthouse mechanism. It is a plasma system capable of state changes. Mode changing and nulling are still not fully understood. They may involve global reorganizations of magnetospheric currents. The changes can happen quickly compared with the age of the star, suggesting that the plasma environment has multiple stable or semi-stable configurations. Even ordinary pulsars, far less dramatic than magnetars, remain active research subjects. Rotating radio transients add another complication. They emit detectable radio bursts, only occasionally, sometimes with long gaps between pulses. They may be related to pulsars seen under unusual conditions or represent a distinct part of neutron star behavior. Their existence warns against assuming that regular pulses are the only way radio neutron stars can appear. The zoo of neutron star behavior is therefore broader than the simple categories suggest. Pulsars, millisecond pulsars, magnetars, X-ray binaries, central compact objects, rotating radio transients, isolated thermal emitters, and merger remnants may all be connected by evolution. Magnetic field, environment, and selection effects. The same basic object can appear under many names because observation catches it at different moments. At the center of all these names is a compact remnant formed because gravity won most of the battle, but not all of it. The star did not remain a star like the Sun. It did not collapse fully into a black hole. It stopped at nuclear density, held up by forces that only matter under extreme compression can provide. That stopping point creates the entire subject. The boundary with black holes is especially interesting because it is not only a mass boundary. Rotation and temperature can temporarily support remnants that would otherwise collapse. A merger can produce a hypermassive neutron star held up by differential rotation and thermal pressure. As it cools and redistributes angular momentum, collapse may follow. The object exists in a transitional state, briefly resisting its own gravity. Such short-lived remnants may power gamma-ray bursts, kilonova components, and winds that affect element formation. The lifetime of the remnant changes the amount of neutrino irradiation, the composition of ejecta, and the energy injected into surrounding material. A difference of milliseconds or seconds can change the visible event for days. Extreme astrophysics often turns tiny timescales into large consequences. The formation of jets in neutron star mergers is still an active field. Short gamma-ray bursts are associated with compact mergers, but launching a relativistic jet through merger debris requires the right conditions. A black hole with an accretion disk is one possibility. A short-lived magnetized neutron star may also contribute. Observations of jet structure after GW 170817 helped refine these models. That jet was not pointed exactly at Earth. The gamma-ray burst was weaker than it would have been on axis, and later radio and X-ray observations traced the afterglow as the jet interacted with surrounding material. This geometry taught astronomers that viewing angle matters enormously. The same merger seen from another direction could look brighter, faster, and very different. The universe does not label its events for us. A short gamma-ray burst may be a neutron star merger. A brief gamma-ray spike may be a magnetar giant flare in a nearby galaxy. A faint X-ray point may be a cooling neutron star, a background active galaxy, or something else. Classification is an argument built from evidence, not a tag attached at the source. This is why multi-wavelength follow-up matters. A gamma-ray trigger can be localized poorly at first. X-ray telescopes search for afterglows. Optical telescopes search for fading transients. Radio telescopes watch for delayed emission. Spectroscopy reveals redshift or elemental signatures. Each layer reduces ambiguity. Without follow-up, many events would remain only brief flashes in a detector log. For magnetars, the absence of a long afterglow can distinguish a giant flare from a cosmological gamma-ray burst. A nearby host galaxy with active star formation can strengthen the case. A lack of gravitational wave signal can matter if the event might otherwise be a compact merger. The final interpretation may still carry caution, but it becomes more persuasive as independent clues align. A quiet control room after a trigger does not mean the event is quiet. It means the evidence has entered a different phase. The burst has passed. The sky has moved on. Now the work is calibration, localization, comparison, modeling, and publication. The cosmic violence becomes a spreadsheet, a spectrum, a likelihood contour, and eventually a sentence in a paper. The contrast can feel strange, but it is how astronomy survives distance. We cannot go to a magnetar. We cannot scoop matter from a neutron star core. We cannot replay a merger from another angle. We can only build instruments, catch what arrives. and test interpretations against the record. The record is improving. New radio surveys find more pulsars and transients. X-ray missions time neutron stars with better precision. Gamma-ray monitors continue to watch for rare flares. Gravitational wave detectors improve sensitivity. Future observatories will see more kilonovae, better localize fast transients, and perhaps detect signals that are now below threshold. With more data, some mysteries will narrow. The equation of state will be constrained further. The rate of magnetar giant flares will be estimated more accurately. The connection between magnetars and fast radio bursts will become clearer, though likely not simple. The population of neutron star mergers will grow from a few events into a statistical sample. Other mysteries may deepen because better instruments often reveal complexity rather than simplicity. More bursts may show more variety. More hotspot maps may reveal more unusual magnetic geometries. More mergers may produce outcomes that do not fit the cleanest models. This is normal. A real universe rarely behaves like the first diagram drawn to explain it. The danger in describing neutron stars is to make them sound like exceptions to physics. They are not exceptions. They obey physics with unusual severity. Gravity, quantum mechanics, nuclear forces, electromagnetism, thermodynamics, and relativity all operate there together. The extremeness comes from the conditions, not from a violation of the rules. A neutron star does not break physics. It tests the edges where our equations are hardest to apply. The same is true of magnetars. Their fields do not make them supernatural. They make them rare and powerful natural objects whose behavior is still being mapped. The discipline is not awe replacing knowledge. It is awe being disciplined by measurement. The most extreme object in space is not always the largest. A galaxy cluster may contain thousands of galaxies. A supermassive black hole may contain billions of solar masses. A void may stretch across hundreds of millions of light years. A neutron star is tiny by comparison, but it concentrates mass, gravity, magnetic field, rotation, and nuclear density into a volume so small that scale becomes inverted. That inversion is part of their fascination. A city-sized star can outshine a nebula in X-rays. A millisecond pulse can identify an object across the galaxy. A crust shift on a magnetar can be detected by spacecraft near Earth. A pair of remnants smaller than counties can shake spacetime across the cosmos. Smallness does not mean weakness when density is extreme. The phrase most extreme objects in space, therefore, has a specific meaning here. It does not mean the loudest in a cinematic sense. It means matter pushed to nuclear density, gravity strong enough to bend light significantly, magnetic fields strong enough to dominate emission, and rotation fast enough to turn stellar remnants into clocks. These are measurable extremes. To understand them, one has to move between scales repeatedly. A collapsing iron core, a neutrino flood, a supernova remnant expanding through a nebula, a 20-kilometer star, a magnetic field stretching far into space, a radio pulse crossing thousands of light years, a merger enriching a galaxy with heavy elements. The same object connects all of these scales. The connection to the rest of the universe is not decorative. Neutron stars return material to space through mergers. They energize nebulae. They test gravity. They probe nuclear physics. They may contribute to fast radio bursts. They serve as clocks for timing arrays. They are part of the life cycle of galaxies because massive stars are part of that cycle. Massive stars form in molecular clouds, live quickly, and die violently. Their remnants become neutron stars or black holes. Their explosions stir the interstellar medium. Their heavy elements enter new clouds. Some of those clouds form planetary systems. The dense remnant left behind may seem isolated, but it is one stage in a longer cosmic recycling of matter. In a processed image of a star-forming galaxy, young massive stars can appear as blue knots or infrared bright regions hidden by dust. In those regions, Future neutron stars are being made indirectly, inside stars that have not yet died. The galaxy is not only a collection of stars, it is a factory of remnants, some of which will become pulsars, magnetars, or merging binaries millions of years later. Starburst galaxies like M82 are especially relevant because they produce massive stars rapidly. More massive stars means more core collapse supernovae, and more supernovae means more young neutron stars and possible magnetars. When a brief gamma-ray event appears from such a galaxy, the environment becomes part of the interpretation. The host galaxy is not background scenery, it is evidence. The Milky Way is quieter than a starburst galaxy, but it still forms massive stars in spiral arms, clusters, and associations. Regions like the Carina Nebula, Cygnus, and the inner galaxy contain young massive populations that will seed future remnants. Some of the neutron stars now observed were born in similar regions long ago and have since moved away. Tracing a neutron star back to its birthplace can be difficult. Proper motion, distance uncertainty, and age estimates all matter. A pulsar may have traveled far from its remnant. A remnant may have faded. A cluster may have dispersed. The birth path becomes a reconstruction, not a direct record. Still, the galaxy keeps clues. Supernova remnants mark recent deaths. Pulsar velocities point backward. Star clusters reveal where massive stars formed. Elemental abundances in gas show past enrichment. Neutron stars are small, but their existence is tied to these larger patterns of galactic evolution. The interior of a neutron star remains the most inaccessible part of the story. The surface can emit, the magnetosphere can flare, the orbit can produce gravitational waves. The core itself is hidden behind density, gravity, and distance. The best probes are indirect, mass, radius, cooling, glitches, oscillations, and mergers. Each one touches the core from outside. If the core contains superfluid neutrons, that changes heat capacity and rotational behavior. If protons are superconducting, magnetic fields thread the core differently. If exotic particles appear, they may soften the equation of state or open faster cooling channels. These are not free inventions. They are specific possibilities that must live within observational constraints. The phrase nuclear pasta may sound playful, but it names a serious theoretical possibility. At densities near the bottom of the crust, nuclei may arrange into rods, slabs, and more complex shapes due to competition between nuclear attraction and electric repulsion. These structures could affect the crust's strength, neutrino opacity, and transport properties. They may be hidden in every neutron star crust, shaping behavior from below. The crust may be only a kilometer or so thick, depending on the star, yet that thickness contains a transition from ordinary nuclei to exotic nuclear geometries and finally to the fluid core. A kilometer is a short walk on Earth. On a neutron star, it is a descent through pressure regimes that convert matter into unfamiliar forms. The geography is small, but the physics changes enormously. If a mountain on Earth rises kilometers high, it does so because rock can support that shape under Earth's gravity. On a neutron star, gravity is far stronger, so the surface is forced towards smoothness. Even if the crust is incredibly strong, the allowed irregularities are limited. The star is not a rugged world of towering peaks. It is a compact body where gravity makes topography a subtle question. The atmosphere, if present, may be thinner than a human hand is wide, yet it controls the emerging spectrum. Hydrogen atmospheres produce different X-ray colors than carbon or heavy element atmospheres. In some young neutron stars, carbon atmosphere models have been considered to explain observed emission. The smallest layer can change the largest inference, including the estimated radius. This is why astronomers are careful about model assumptions. A radius estimate depends on distance, absorption, atmospheric composition, magnetic field, temperature distribution, and relativistic light bending. The result may be robust within a model family, but the model family must be justified. The star does not hand over its radius. It lets observers infer it through a chain of reasoning. Masses can sometimes be measured more directly in binaries. Radio timing of pulsars in binary systems reveals orbital parameters with extraordinary precision. Relativistic effects such as periastron advance, Shapiro delay, and orbital decay can yield component masses. Some of the strongest constraints on the equation of state come from heavy pulsars whose masses are known to be around 2 solar masses. Shapiro delay occurs when pulses pass through the gravitational field of a companion and arrive slightly later than they would otherwise. Measuring that delay can reveal the inclination and masses in a binary system. It is a small effect, but pulsar timing can be so precise that small effects become measurable. General relativity becomes a tool for weighing stars. The fact that neutron stars can be weighed this way is remarkable. No scale holds them. No orbiting spacecraft measures them from nearby. Their masses are extracted from time delays, orbital motion, and relativistic corrections in pulses crossing interstellar space. The method is indirect, but it is not vague. It is one of the most precise parts of the field. Radius is harder. That is why nicer, thermonuclear X-ray burst modeling, quiescent low-mass X-ray binaries, and gravitational wave tidal effects all matter. Each method has different systematics. Agreement among methods strengthens confidence. Tension among methods reveals where assumptions may be incomplete. The maximum mass remains critical. If a neutron star above a certain mass is observed, every equation of state that cannot support it must be rejected. If future observations find a very massive neutron star, the implications would be immediate. If no such stars appear despite extensive searches, that absence also informs the likely boundary with black holes. The boundary may not be sharp in observation, because measuring compact object masses is difficult. Some objects in the mass gap between known neutron stars and black holes have been proposed in gravitational wave detections. Whether they are heavy neutron stars, light black holes, or products of unusual evolution is still debated case by case. The classification depends on mass, spin, tidal signatures, and electromagnetic counterparts. In this sense, neutron stars are central to one of astronomy's most practical classification problems. What counts as a neutron star at the high mass end? What counts as a black hole at the low mass end? The answer is not only naming. It affects supernova theory, dense matter physics, binary evolution, and merger rates. The path forward is not a single telescope. It is an accumulation of different measurements. More massive pulsars. Better radius estimates. More neutron star mergers. Better post-merger sensitivity. More magnetar outbursts with simultaneous radio and X-ray coverage. More polarization measurements. More long-term timing. The object is too complex for one method to dominate completely. A radio dish turning beneath a dark sky is part of this path. So is a small X-ray telescope mounted on the space station. So is a gamma-ray monitor waiting for a millisecond spike. So are kilometer-scale interferometers measuring changes smaller than an atomic nucleus relative to their arms. Neutron stars require an astronomy of patience and readiness at the same time. Patience matters because pulsars reveal themselves over years. A timing solution improves as more pulses are counted. Glitches may occur rarely. Binary orbits precess slowly. Cooling after outbursts can take months. The star changes on timescales, from milliseconds to millennia, and the observing strategy must match the process. Readiness matters because magnetar flares and mergers do not wait. A giant flare may last less than a second. A kilonova fades over days. A fast radio burst is gone in milliseconds. Automated alerts, wide-field monitors, and rapid follow-up networks exist because the universe sometimes gives only one chance to catch the early light. The contrast between patience and speed defines modern transient astronomy. Watch for years. React in seconds. Archive everything. Revisit old data. Build models that can change when a new event arrives. Neutron stars sit at the center of this workflow because so much of their behavior is sudden, and so much of their meaning comes from long context. A magnetar in outburst may be followed for months after the initial burst. Its flux decays. Its spectrum changes. Its pulse profile evolves. If dust scattering rings appear, they expand in images as delayed photons arrive from different paths. The outburst becomes a three-dimensional probe of the star, the dust, and the line of sight. Dust scattering rings are especially visual. An X-ray burst travels outward. Some photons fly straight to the telescope. Others scatter off dust clouds and take longer paths. They arrive later and appear as expanding rings around the source. The rings are not physical shells around the magnetar. They are echoes produced by geometry between the burst, the dust, and the observer. Such details keep space from becoming empty. The path from a magnetar to Earth includes interstellar dust, plasma, magnetic fields, and gravitational curvature. A photon does not simply cross a blank stage. It moves through a galaxy with structure. That structure alters the signal, and sometimes becomes visible because of the signal. The same is true for gravitational waves, though in a different way. They pass through matter almost without interaction, which is why they can escape dense regions and travel across the universe. But their weakness makes them difficult to detect. A neutron star merger can release enormous energy in gravitational waves, yet by the time the waves reach Earth, the strain is almost unimaginably small. The detectors respond not by catching particles, but by measuring changes in distance. Laser beams travel down long arms and return. Interference patterns shift when spacetime stretches one arm slightly more than the other. The signal is compared against templates from general relativity. When a neutron star in spiral appears, its chirp carries masses and tidal information encoded in the changing frequency. The word chirp is appropriate because the frequency rises as the orbit tightens. But this is not sound traveling through space. It is a gravitational waveform translated into a frequency humans can hear for demonstration. The original signal is space-time curvature changing at the detector. The audio is a representation, useful but not literal. Representations are everywhere in this subject. A pulsar's radio beam becomes a folded profile. A magnetar flare becomes a light curve. A hotspot becomes a model map. A merger becomes a strain waveform. A kilonova becomes a color evolution plot. The star is always mediated by translation, and the translations must be handled carefully. The most honest way to describe neutron stars is therefore neither cold nor mystical. It is precise and open. They are known through evidence. They are surrounded by uncertainties. They are extreme because gravity and nuclear matter make them extreme. They matter because they connect stellar death to fundamental physics, transient astronomy, and the chemical history of galaxies. The opening trace on the monitor, the one that looked like rhythm instead of a star, is part of a much larger map. It may belong to a pulsar rotating steadily. It may belong to a magnetar entering an active state. It may be the afterglow of a merger, the cooling of a crust, the pulse of a hotspot, or the delayed echo of a burst through dust. The interpretation depends on context. Context is built slowly. Coordinates are checked. Periods are measured. Spectra are fitted. Old observations are searched. Other telescopes are asked what they saw at the same time. The result is a picture assembled from instruments that never see the object as a nearby world, but still manage to make it scientifically present. A neutron star does not need to be large to dominate the physics around it. Its gravitational field controls nearby orbits. Its magnetic field shapes plasma. Its rotation powers beams. Its surface releases accretion energy. Its merger can build heavy elements. Its timing can test relativity. Its interior can reject theories of matter. All of this emerges from a remnant smaller than many cities. Magnetars are the most magnetic members of this family, but they are not separate from the story of neutron stars. They are one possible outcome of core collapse, shaped by rapid rotation, magnetic amplification, and early evolution. Their flares are spectacular because the stored magnetic energy is immense, but the deeper story is the coupling between field, crust, magnetosphere, and radiation. When a magnetar is quiet, it is still extreme. The field remains, the crust remains stressed, the star continues to spin down, heat leaks outward, particles move through the magnetosphere. The fact that no burst is seen during a given observation does not mean nothing is happening. It means the star is below the threshold of our instruments or between episodes of visible activity. When it erupts, the hidden system becomes briefly obvious. A spike in gamma rays, a changed X-ray pulse, a radio burst that may or may not accompany it, a dust echo, a fading tail modulated by rotation. The star does not explain itself, but it gives enough clues for models to be tested. The same is true of mergers. The inspiral gives masses. The tidal imprint gives structure. The gamma-ray burst gives a jet. The kilonova gives ejecta and nucleosynthesis. The afterglow gives geometry. No one signal is the whole event. Together, they form a temporary observatory around a collision that happened far beyond direct reach. There is humility in this kind of knowledge. Not the humility of surrender, but the humility of method. Astronomers know that a neutron star is not fully visible from Earth. They know the models depend on assumptions. They know better instruments may change the answer. That is why the field remains alive. The unknown has edges, and those edges can be measured. A future observation may catch a galactic magnetar giant flare with modern instruments ready across the spectrum. It may detect gravitational waves from a nearby neutron star merger with a clear post-merger signal. It may map a pulsar hotspot with better precision. It may find a heavier neutron star or rule out one. Any of these would change the constraints. The universe may also produce events that do not fit the expected categories. A transient that looks like a magnetar flare but has an afterglow. A merger with unusual ejecta. A radio burst from a source that does not behave like known magnetars. In those moments, the science will not be weaker because it hesitates. It will be stronger if it names the uncertainty clearly. For now, the known picture is already remarkable. Massive stars die. Some leave neutron stars. Some neutron stars beam like clocks. Some are spun up by companions. Some accrete and burst. Some carry magnetic fields so strong that field decay powers high-energy eruptions. Some merge and forge heavy elements. Some may be quiet and unseen, moving through the galaxy with no beam pointed toward Earth. Every part of that picture comes from evidence gathered at a distance. The evidence is scattered across wavelengths and instruments, but it converges on the same physical idea. Matter can be compressed to nuclear density and remain, for a time, a star with a surface. Around that surface, gravity, rotation, and magnetic fields create behaviors that look varied because the same extreme object is being viewed under different conditions. Near the end of a massive star's life, the core does not know that it will become a named object in a catalog. It simply runs out of support. Gravity acts. Particles are forced together. Neutrinos escape. The outer layers are thrown into space. A remnant remains. Later, perhaps thousands of years later, a telescope on Earth or in orbit receives a pulse and begins the work of understanding what was left behind. That work is still unfinished. It will remain unfinished for a long time, because neutron stars occupy a place where observation is difficult and theory is demanding. But unfinished does not mean vague. It means every new measurement has somewhere to go. A better radius narrows dense matter. A flare tests magnetic stress. A glitch probes the interior. A merger tests gravity and nuclear physics at once. Another way to understand neutron stars is to follow the last hours of the star that makes them. The outer layers may still look like a normal massive star, swollen and luminous, while the core is already changing too fast for the surface to show it. Deep inside, silicon burning builds iron group elements in a shell structure that has been compared to layers in an onion, though the comparison is quiet compared with the reality. The core is not calmly arranged. It is hot, turbulent, and close to collapse. The collapse begins when support fails locally, then spreads through the core as gravity overwhelms pressure. Electrons that once helped hold matter apart are driven into protons through electron capture. This reduces pressure and produces neutrinos. The loss of pressure makes collapse faster, and the production of neutrinos becomes one of the dominant channels by which energy leaves the core. In a supernova, most of the gravitational binding energy does not emerge as visible light. It escapes as neutrinos. That fact became more than theory with supernova 1987A in the Large Magellanic Cloud. Detectors on Earth recorded a small number of neutrinos from the explosion before the light curve fully developed. The number was tiny by ordinary standards, but the implication was enormous. Neutrinos from a collapsing core had crossed about 160,000 light-years and confirmed that the central engine of a core collapse supernova was not merely bright gas, but a compact gravitational event. The remnant of supernova 1987A has been searched for signs of the compact object that should have formed. The debris is still thick, evolving, and complicated. Observations at different wavelengths have revealed dust, molecular emission, shock interaction, and possible indirect hints of a hidden neutron star, but the central remnant has not been as straightforward as the Crab pulsar. This is a useful caution. Even nearby supernovae do not always hand over their cores quickly. A newborn neutron star is expected to be intensely hot, with temperatures far above anything associated with ordinary stellar surfaces. Much of that heat disappears through neutrino cooling in the early stages. Later, photons from the surface dominate. The cooling history depends on the interior composition, superfluidity, crust thickness, envelope composition, and magnetic field. A cooling neutron star is therefore not just a fading ember, it is a diagnostic of matter under pressure. The first few minutes after birth may also shape the magnetic future. If the newborn star rotates extremely rapidly, convection and differential rotation can amplify magnetic fields through dynamo action. This is one proposed route to magnetar formation. The exact requirements are still debated, and not every massive star core becomes a magnetar. The difference between an ordinary pulsar and a magnetar may be decided by conditions during a brief violent interval no telescope can watch directly inside the star. A massive star's environment may leave clues. Magnetars are often associated with regions where massive stars have recently formed, which fits their expected youth. Some lie in or near supernova remnants. Others have no obvious remnant, either because the remnant has faded, the association is difficult, or the magnetar has moved. The absence of a remnant does not automatically mean old age, but it complicates the story. Age estimates for neutron stars come in several forms, and they do not always agree perfectly. A characteristic age can be calculated from spin period and spin-down rate under assumptions about magnetic braking. A supernova remnant can provide an independent age if the association is secure. A cluster age can constrain the progenitor. Thermal cooling gives another clue. Disagreements between these clocks can reveal that the assumptions are incomplete. One reason characteristic age can mislead is that a neutron star may not have been born spinning much faster than it spins now, or its magnetic braking may have changed. Magnetars can have variable spin-down torques during outbursts. Accretion can spin a neutron star up. Binary interaction can alter its history. A period and a period derivative are powerful, but they are not a full biography. Magnetic braking itself is a physical process, not just a formula. A rotating magnetic dipole radiates energy, and the surrounding plasma carries energy and angular momentum away. Field lines may open and close. Currents flow through the magnetosphere. The torque depends on the field geometry and plasma state. When that state changes, the star's spin down can change too. This helps explain why magnetar timing can look noisy compared with ordinary rotation-powered pulsars. Outbursts can coincide with changes in torque. The external magnetic field may twist and untwist. Particle winds may strengthen. The star's rotation records these changes as irregularities. Timing noise is not just inconvenience. It is a sign that the magnetosphere is alive with evolving currents. The catalog of magnetars is small compared with the catalog of radio pulsars, but each object has its own temperament. Some are persistent X-ray sources, some produce repeated short bursts, some have produced giant flares. Some have emitted transient radio pulses, some have shown outbursts after years of quiet. The category is unified by magnetic energy, but the behavior is not uniform. SKR 052666, associated with the Large Magellanic Cloud, produced the famous March 5, 1979 event, one of the earliest giant flares recognized from a magnetar. It helped establish that at least some short high-energy bursts could originate from compact objects in nearby galaxies rather than from the distant cosmological gamma-ray burst population. The event's repeating tail, modulated by the object's rotation, was a clue to a neutron star source. SKR 1900+14 produced a giant flare in 1998. Like other giant flares, it showed an intense initial spike followed by pulsating emission. Events like this built the observational foundation for magnetar theory before the term became widely familiar outside astrophysics. They also showed that giant flares were rare, separated by years or decades in the record, so every case became important for understanding the class. By the time SKR 180620 erupted in 2004, high-energy astronomy had more instruments capable of recording the event in detail. The flare's brightness caused problems for detectors because it was too intense for some systems to handle cleanly. This is an unusual kind of measurement difficulty. Astronomers often fight faintness. In this case, the universe delivered a signal so strong that instruments designed for high-energy events had to be interpreted with care. The oscillations reported after the 2004 flare opened the possibility of magnetar astroseismology. If a flare excites torsional modes in the crust or global magnetoelastic oscillations, their frequencies may depend on the crust composition, magnetic field strength, and coupling to the core. The interpretation is difficult because the magnetic field links regions together, but the possibility remains compelling. A distant flare may let researchers hear how a neutron star vibrates. The word "hear" again is representation. No sound crosses space from the magnetar to Earth. The oscillations appear as variations in X-ray brightness. Humans can translate frequencies into sound for illustration, but the measurement is electromagnetic. The important point is not literal sound. It is that periodic structure in the light may encode mechanical motion in the star. This same caution applies when gravitational waves are played as audio. A chirp from a merger can be shifted into the range of hearing, and it is useful because humans recognize rising pitch. But the detector measured strain, not air pressure. The universe gives us signals, and humans choose translations. Good science remembers the difference. Neutron stars make this distinction unavoidable because none of their most important messengers are visible to the unaided eye. The Crab Nebula can be seen with telescopes in optical light, but the pulsar's full behavior requires radio, X-rays, and gamma rays. Magnetar bursts require high-energy detectors. Mergers require interferometers and rapid follow-up. The subject begins where ordinary sight ends. The surface emission from a cooling neutron star can be extremely faint in optical light, but stronger in X-rays. A neutron star may therefore be invisible in a deep optical frame, while present in a Chandra image. Astronomers align images from different telescopes, check astrometry, compare expected positions, and ask whether the X-ray point belongs to the remnant or to an unrelated background source. Astrometry can decide whether a compact object sits near the center of a supernova remnant or has moved away from it. Proper motion can estimate velocity. If the object appears offset, the offset can imply a kick at birth. But projection effects, distance uncertainty, and remnant asymmetry complicate the inference. A simple image becomes a geometry problem across thousands of years. Sometimes, a pulsar wind nebula points back toward the birthplace. A cometary tail or bow shock can indicate direction of motion. The neutron star moves supersonically through interstellar gas, and its particle wind is swept behind it. The shape is not a decorative feature. It is a record of motion, wind pressure, ambient density, and magnetic field. The Guitar Nebula, produced by a fast-moving pulsar, is an example of how strange these records can appear. Its shape comes from the pulsar's bow shock interacting with varying interstellar material. The name comes from the outline in images, but the physics is a compact star racing through gas and driving a shock front ahead of it. Even whimsical names often hide precise dynamics. The naming of neutron star objects can feel cryptic because many are known by coordinates. ScarJO 7373039, SCAR 1935 plus 2154, 1E2259 plus 586. These names are not meant to be poetic. They are practical labels that encode position, survey, or object type. In a field where thousands of compact sources may be cataloged, coordinates become the most reliable way to point back to the evidence. A coordinate, however, can become familiar when enough is learned. The Crab pulsar is more than PSR B0531 plus 21 because history, images, and repeated observations have made it vivid. A SCAR 180620 is more than a coordinate because of the 2004 flare. GW 170817 is more than a gravitational wave label because it opened multi-messenger astronomy with neutron stars. The name accumulates meaning from evidence. There is also an important difference between isolated neutron stars and those in dense environments. In a supernova remnant, surrounding debris can absorb or scatter radiation. Near the galactic center, plasma can scatter radio waves severely. In a globular cluster, many compact objects may crowd the field. In an X-ray binary, the accretion disk can dominate the light. The neutron star is often not alone observationally, even if it is physically compact. Accretion can create some of the most dramatic surface phenomena. In a low-mass X-ray binary, gas from a companion star spirals inward and accumulates on the neutron star surface. Hydrogen and helium can build up until conditions trigger runaway nuclear burning. The result is a Type 1 X-ray burst, a sudden brightening that can last seconds to minutes and then fade as the surface layer cools. These bursts confirm the presence of a surface, because the thermonuclear fuel burns on that surface. Black hole candidates do not show the same kind of surface burning. The comparison is one of the ways astronomers distinguish neutron stars from black holes in accreting systems. The star's compact surface is not directly imaged, but it announces itself through nuclear flashes. Some X-ray bursts show photospheric radius expansion. The radiation pressure becomes strong enough to lift the outer layers of the neutron star atmosphere temporarily. As the photosphere expands and contracts, the spectrum changes. These events have been used to estimate distances and radii, though the method depends on composition, anisotropy, and other assumptions. Even a thermonuclear flash becomes a measuring device. Accretion-powered millisecond X-ray pulsars show pulses because material is funneled by magnetic fields onto rotating hotspots. Their discovery connected accreting neutron stars to the recycled millisecond radio pulsars that appear after accretion ends. The evolutionary link is not just theoretical. It is observed through systems that show the spin-up process in action. Some transitional millisecond pulsars switch between accretion-powered X-ray states and rotation-powered radio pulsar states. These objects are especially valuable because they reveal a neutron star moving between phases that were once treated separately. The magnetosphere, accretion disk, and companion interact in a shifting balance. The same star can appear as different kinds of source depending on the state of the system. This state-changing behavior is another warning against rigid categories. A neutron star can be an accretor, a radio pulsar, an X-ray source, and a gamma-ray emitter at different times. The classification depends partly on when the telescope looks. Long-term monitoring is therefore not a luxury. It is necessary to avoid mistaking a temporary state for an identity. Gamma-ray pulsars, many discovered or characterized by the Fermi Gamma-ray Space Telescope, expanded the known pulsar population. Some are radio-quiet or have radio beams that miss Earth. Gamma-ray emission often comes from outer regions of the magnetosphere, so the beam geometry differs from radio emission. Seeing a pulsar in gamma rays can reveal objects that radio surveys alone would miss. Fermi also showed that millisecond pulsars are important gamma-ray sources. These old recycled neutron stars can remain energetic enough to produce high-energy emission. In globular clusters, combined gamma-ray light may come from populations of millisecond pulsars. Again, neutron stars appear not only as individual objects, but as collective contributors to a galaxy's high-energy glow. The high-energy sky is full of compact objects, but neutron stars have a particular signature when timing is available. A black hole accretion disk can flicker. A white dwarf can pulse or rotate, but a neutron star pulsar can maintain a coherent period that reveals the spin of a compact surface. Timing turns a distant point source into a rotating body. Timing also reveals binary companions through Doppler shifts. As a pulsar orbits, pulses arrive early or late, depending on whether the star is moving toward or away from Earth. These delays map the orbit. If the companion is another neutron star, a white dwarf, or a main sequence star, the orbital solution can reveal masses and geometry. The pulse train becomes a ruler and a clock. In some systems, eclipses occur as material from the companion blocks the radio beam. In Black Widow and Redback pulsars, energetic winds from the neutron starstrip material from a low-mass companion. The names are colorful, but the physics is harsh. A recycled pulsar ablating the star that helped spin it up. Binary evolution can be intimate and destructive. The companions in such systems may eventually be reduced to very low masses, leaving isolated millisecond pulsars. This is one proposed route for some solitary recycled pulsars. It shows that neutron stars do not merely survive stellar evolution. They can reshape the evolution of other stars, stripping, heating, and sometimes nearly destroying their partners. At the strongest magnetic fields, even atomic structure near the surface may be altered. Electrons occupy quantized states differently under intense fields, and opacities change. This affects atmosphere models and radiative transfer. A magnetar atmosphere is not a simple hot gas. It is a plasma under magnetic conditions where familiar approximations may fail. Radiative transfer in such fields is difficult because photons can scatter resonantly off-charged particles and change polarization states. The magnetosphere can reprocess surface emission before it escapes. Observed X-ray spectra may therefore combine thermal radiation from the surface with non-thermal components produced by magnetospheric currents. Separating these contributions is part of magnetar modeling. The quantum electrodynamic field scale, sometimes called the critical field, is around 4.4 times 10 to the 13 Gauss. Magnetars can exceed this. Above that scale, effects that are negligible in ordinary magnetic fields become important. The vacuum itself behaves as a medium for polarization. This is not science fiction. It is a prediction of quantum physics made testable by extreme astrophysical objects. Polarization observations of isolated neutron stars and magnetars are therefore more than technical additions. They probe how light moves through strong fields and how emission regions are arranged. The Imaging X-ray Polarimetry Explorer and future missions can add constraints that brightness and spectra alone cannot supply. A photon carries not only energy and arrival time, but orientation. The surface temperature distribution of a neutron star can also tell a magnetic story. Heat moves more easily along magnetic field lines than across them. Strong fields can insulate some regions and connect others. The result may be hot polar caps, warm belts, or asymmetric patterns. When the star rotates, those patterns become pulse shapes. A pulse shape can look simple in a plot, but it contains many layers. The star's compactness bends light. The atmosphere beams radiation differently at different angles. The hotspot may not be circular. The observer may view the spin axis from an oblique angle. Interstellar absorption removes some photons. The detector has its own response. The final curve is the product of all these ingredients. This is why independent measurements are so valuable. If radio timing gives a mass, X-ray modeling can focus on radius. If a distance is known from parallax, luminosity becomes more secure. If polarization constrains geometry, pulse profile degeneracies can shrink. The goal is not to trust one signal blindly, but to make different signals converge. The future of neutron star science will probably be built from convergence. Better radio surveys will find more relativistic binaries. More sensitive gravitational wave detectors will catch more mergers and perhaps post-merger oscillations. X-ray timing and polarization will refine surface maps. Infrared telescopes will follow kilonovae through dust and distance. Nuclear experiments will improve the theoretical side of the equation of state. Even then, neutron stars may keep surprises. The first pulsars were surprises. Magnetars were not obvious from ordinary pulsar theory. Fast radio bursts were unexpected, and their connection to magnetars emerged only after years of uncertainty. Gravitational waves from a neutron-star merger arrived with light and heavy elements. The field has repeatedly advanced because the sky did something measurable that did not fit the simplest expectation. That is the difference between mystery and vagueness. A vague mystery can absorb any answer. A scientific mystery becomes sharper when evidence accumulates. Neutron stars are full of sharp mysteries. Their masses are measured. Their periods are measured. Their flares have dates and light curves. Their mergers have waveforms. The unknown sits inside a frame built by data. It is possible to imagine standing near one only as a thought experiment, because no material observer could survive. Radiation, gravity, and tidal forces would make the environment inaccessible. A spacecraft would be destroyed long before reaching the surface in any ordinary mission scenario. The closest approach we have is not travel, but measurement, and measurement has carried us surprisingly far. A human-made detector can be more powerful than proximity in one sense. It can sit safely near Earth and receive signals from many neutron stars, not just one. It can watch the sky for years. It can compare populations. It can coordinate with other instruments. It cannot touch the star, but it can turn distance into a survey. The result is a map of behavior across the galaxy. Young energetic pulsars near supernova remnants. Old millisecond pulsars in binaries and clusters. Magnetars concentrated towards star-forming regions. X-ray binaries in the disk and globular clusters, merging systems rare but cosmologically important. The map is incomplete, but it has structure. That structure connects to the life cycle of matter. The calcium in bones, the iron in blood, the iodine in thyroid tissue, the gold in circuits and jewelry, all belong to histories of stellar nucleosynthesis. Neutron star mergers are part of the story for some of the heaviest elements. Supernovae are part of the story for many others. Compact remnants are not remote from chemistry. They are part of why the periodic table exists in the universe as it does. This connection should not be overstated into sentimentality. A specific atom on Earth cannot usually be traced to a named merger. Galactic mixing is complex, and many generations of stars contributed to the solar system's birth cloud. But the physical processes are real. Heavy elements require astrophysical sites, and neutron-rich ejecta from neutron star mergers is one of the most important known sites. Meteorites preserve early solar system material that formed long after many such events enriched the galaxy. Laboratory measurements of isotopes, combined with models of galactic chemical evolution, help reconstruct the sources that contributed to the Sun's birth environment. The chain from a neutron star merger to a meteorite slice is long, indirect, and uncertain in detail, but it is a real scientific chain. The universe often works through such chains. A massive star forms from a cloud. It dies and leaves a neutron star. The explosion enriches gas. The neutron star may later merge with another remnant, adding heavier elements. A later cloud incorporates that material. A planetary system forms. Billions of years later, instruments built on one planet detect the kind of event that helped make such planets chemically possible. Neutron stars are therefore both endpoints and beginnings. They are endpoints of massive stellar cores. They are beginnings of pulsar winds, magnetar flares, gravitational wave events, kilonovae, and heavy element enrichment. They are remnants, but not passive ones. Their afterlives are among the most active phases in high-energy astrophysics. This double identity explains why they resist simple description. A neutron star is dead if the standard is fusion. It is alive with behavior if the standard is physics. It can cool, glitch, accrete, flare, merge, emit beams, power nebulae, and test equations. The word remnant is accurate, but it should not imply stillness. At the same time, not every neutron star is spectacular at every moment. Many are faint. Many are quiet. Many are invisible. The extremes that make the subject famous are drawn from a larger population where most objects spend long periods doing little that current instruments can detect. The quiet majority matters because it tells us how remnants age, fade, and fill the galaxy. A complete story must hold both ideas, the rare flare and the long quiet, the millisecond burst and the million-year cooling curve, the dramatic merger and the old pulsar, counted patiently for decades. Neutron stars are not only moments of violence, they are enduring objects, changing slowly until conditions make them briefly bright. This endurance is one reason pulsar timing is so powerful. A pulsar observed today can be observed tomorrow, next year, and decades from now. The period will change, but predictably enough that deviations become meaningful. The object becomes a long-term partner in measurement, a natural clock whose imperfections reveal physics. Magnetars are less cooperative clocks, but their unpredictability is part of their value. When they change, they expose magnetic processes that stable pulsars hide. The best science comes from studying both, the regularity of pulsars and the unrest of magnetars, the steady spin down and the sudden flare, the clock and the storm. These two faces belong to the same family. A magnetar is not a monster separate from neutron star physics. It is neutron star physics with magnetic energy moved to the foreground. A pulsar is not a simple clock separate from plasma physics. It is neutron star physics with rotation moved to the foreground. The labels tell us which engine dominates the observation, not everything the object is. The more instruments improve, the more overlap appears. Radiomagnetars, high magnetic field pulsars, transitional systems, low field magnetars, gamma-ray millisecond pulsars, compact central objects with weak external fields. The old map with clean borders becomes a more continuous terrain. That is not confusion. It is a sign that the observations are becoming rich enough to reveal evolution. Evolution is the quiet backbone of the whole subject. A neutron star is born hot, rapidly changing, and often fast spinning. It cools, it spins down, its magnetic field evolves. It may interact with a companion. It may be recycled. It may become active as a magnetar. It may merge, or it may fade alone. Every observed object is one frame from that long sequence. A catalog can freeze the frame, but the star is not frozen. The pulse period today is not the period at birth. The magnetic field seen externally may not be the field inside. The luminosity during an outburst is not the luminosity in quiescence. The companion may have been different in the past. The remnant may have a future collapse or merger still ahead. That future can be calculated for some binaries. Orbital decay gives a merger time. Some systems will merge within the age of the universe. Others will not. For those that will, the gravitational waves are already being emitted, extremely weak at their current separation, carrying away energy one orbit at a time. The final chirp is only the last seconds of a process that began long before humans existed. When the final chirp arrives at Earth, it will not announce the years of prior decay directly. It will compress the end into a rising waveform. Telescopes will search for light. If a kilonova is found, spectra will be taken. If no light is seen, upper limits will be placed. The event will join a growing sample, and the sample will refine the rates, ejecta masses, and remnant possibilities. This is how the field moves from singular wonder to population science. The first event proves that something happens. The 10th begins to show variation. The 100th reveals distributions. Neutron star astronomy is still young in multi-messenger terms. The sample is small, but it is no longer empty. The next generation of neutron star work will also depend on surveys that are not built for only one object type. Wide-field optical surveys can find kilonova candidates among thousands of changing sources. Radio surveys can uncover pulsars, rotating transients, and fast radio bursts. X-ray monitors can catch outbursts from sources that were previously quiet. A neutron star may enter the record through any one of these doors. Survey astronomy changes the psychology of discovery. Instead of pointing at one known target and asking one question, instruments scan enormous parts of the sky and produce streams of alerts. Most alerts are ordinary variable stars, active galactic nuclei, supernovae, or known objects. Hidden among them may be the rare signal, a nearby kilonova, a magnetar flare, a new pulsar, or a transient that does not fit existing categories. Machine learning and automated pipelines help sort the flow, but the final interpretation still depends on physical understanding. A classifier can rank candidates. It cannot by itself explain a neutron star merger or a magnetar outburst. Human judgment, theoretical models, and follow-up observations remain necessary, especially for rare events where the training examples are few. The Vera C. Rubin Observatory, gravitational wave detector upgrades, radio arrays such as Meerkat and the Square Kilometra Array Pathfinders, and future X-ray missions all belong to this broader change. The sky is becoming less like a set of still images and more like a monitored environment. Neutron stars, because they flare, pulse, merge, and change state, are exactly the kind of objects that benefit from watching the sky as a process. Still, more data will not remove the need for careful language. A brighter transient is not automatically a magnetar. A short gamma-ray burst is not automatically a merger. A periodic signal is not automatically a pulsar until interference, satellites, and instrumental effects are excluded. The more rapidly alerts move, the more important scientific caution becomes. There is also the challenge of public language. Neutron stars are often described through extremes because extremes attract attention. The strongest magnets, the densest stars, the fastest clocks. Those descriptions are often true in broad form, but they can become empty if separated from evidence. The real force of the subject lies in how those extremes are measured. A magnetic field inferred from spin-down is not the same as a handheld magnet reading. A density estimate comes from mass and radius constraints, not from a sample in a container. A merger waveform is not a sound recorded by a microphone. A kilonova color is not simply a painted glow. Each statement has a method behind it, and the method is what keeps the wonder from drifting into exaggeration. The most useful comparisons are the ones that eventually return to the measurement. A neutron star may be city-sized, but the radius is constrained by X-ray modeling, nuclear theory, and gravitational waves. A magnetar may have a field 1 trillion times stronger than ordinary references, but the field is inferred from timing and emission behavior, A flare may release enormous energy, but the number depends on distance, spectrum, and assumed geometry. This carefulness does not make the topic smaller. It makes it more durable. Claims that are tied to measurement can survive correction. If a distance changes, the energy can be revised. If a model improves, the radius can be updated. If a new event breaks a pattern, the category can be reshaped. Science is not weakened by revision when revision follows better evidence. Neutron stars have already gone through such revisions. They began as theoretical possibilities. Pulsars made them visible. X-ray binaries revealed their surfaces and accretion behavior. Magnetars expanded the role of magnetic energy. Gravitational waves made their mergers audible to interferometers. Each stage added new behavior without erasing the earlier picture. The next revision may come from dense matter. If future measurements converge on a narrow radius range, many equations of state will fall away. If a very heavy neutron star is confirmed, the maximum mass will shift upward. If post-merger gravitational waves are detected, the interior may become much less hidden. The core of the star will still not be directly visible, but its allowed forms will become fewer. Another revision may come from fast radio bursts. If many localized repeating bursts are linked to young magnetars in star-forming regions, the magnetar connection will strengthen. If other bursts come from older environments or sources inconsistent with magnetars, the population will diversify. The answer may be that magnetars produce some FRBs, while other engines produce others. Nature often prefers families over single explanations. Magnetar giant flares may also complicate the catalog of short gamma-ray bursts. Some events classified as distant mergers may turn out to be nearby extragalactic magnetar flares. Distinguishing them matters for merger rates and for understanding magnetar activity. It also shows why archival reanalysis remains valuable. A burst recorded years ago can change meaning when models and comparison samples improve. The neutron star itself remains indifferent to these classifications. It rotates, cools, glitches, accretes, or flares according to its physical state. The categories are human attempts to organize signals. They are useful, but they are not the object. The object is the dense remnant, with a history deeper than any single label. A useful way to picture that history is as a chain of transformations. Gas in a molecular cloud collapses into a massive star. The star burns quickly and builds an iron core. The core collapses. A supernova ejects the outer layers. A neutron star forms. The remnant cools, spins, and magnetically evolves. It may interact with a companion. It may become a pulsar, a magnetar, an accretor, or a merger remnant. At each stage, different instruments become relevant. The chain is not guaranteed. A slightly different core may become a black hole. A binary may be disrupted by a supernova kick. A magnetar may fade before humans build telescopes sensitive enough to notice it. A merger may occur in a galaxy too distant for a kilonova to be seen. The observable universe is a selection from all physical outcomes, not the full set. That selection is why humility belongs even in confident narration. We can say neutron stars exist. We can say magnetars have the strongest known magnetic fields among stars. We can say GW170817 was observed in gravitational waves and light. We can say some magnetars produce fast radio burst-like signals. But we should not say every mystery is solved, or every burst has one source, or every interior model is known. The strength of the field is that it can hold certainty and uncertainty together. The existence of neutron stars is certain. The exact composition of their cores is not. The magnetar interpretation is powerful. The details of flare triggering remain debated. The merger origin of many heavy elements is well supported. The relative contribution of different astrophysical sites is still refined. These distinctions are where accurate wonder lives. If the camera were placed far outside the Milky Way, neutron stars would be invisible as individual bodies. The galaxy would show spiral arms, dust lanes, star-forming regions, old stellar populations, and a central bulge. Hidden inside that wide view would be millions of compact remnants, each smaller than a city, most too faint to isolate. The large galaxy and the small remnant belong to the same structure. Zoom inward to a star-forming region, and the future becomes more specific. Massive blue stars illuminate gas. Some will explode. Some cores will collapse into black holes. Others will stop as neutron stars. A few may become magnetars. Binary systems may survive, tighten, and later merge. The future neutron star population is already implied by the massive stars visible now. Zoom inward again, past the supernova, past the expanding remnant, to the compact object itself, and the scale changes completely. The star is no longer a broad sphere like the Sun. It is a dense surface, a thin atmosphere, a crust under strain, a core under unknown pressure, a magnetic field extending outward, and a rotation period written into radiation. A galaxy's stellar evolution has condensed into one object. Then zoom outward through time. The pulse leaves the magnetosphere. It crosses interstellar plasma. It is dispersed, perhaps scattered, perhaps absorbed in some wavelengths. It enters the solar system and reaches a telescope. Electronics convert it into data. Software folds it by period. A human sees a profile rising from noise. The star becomes known not by proximity, but by the survival of a pattern. This is the path every neutron star signal must take. From an extreme physical event to a propagating messenger. From a messenger to an instrument response. From an instrument response to a calibrated dataset. From a dataset to a model. From a model to a cautious statement about the universe. The chain is long, but it is strong enough to let a city-sized remnant become part of human knowledge. The quietest part of the story may be the most important. Somewhere in an archive, there are pulse arrival times that look repetitive to anyone outside the field. To a timing astronomer, they carry spin down, orbital motion, glitches, dispersion changes, and perhaps gravitational wave backgrounds. The same kind of line, repeated for years, can become a map of forces acting across space. Somewhere else, a high-energy detector records nothing unusual for months. That absence is part of the monitoring. Then one day a magnetar emits a burst, and the empty record before it becomes context. How bright was the source before the burst? Did the spectrum change? Was the spin down already shifting? The quiet data become valuable because the flare arrived later. In neutron star astronomy, waiting is not passive. It is how rare events become measurable. It is how periods become precise. It is how glitches are caught. It is how outbursts are placed in history. The instruments are patient because the objects are not obligated to reveal themselves on human schedules. The final understanding may never be as simple as a single answer. Neutron stars are too rich for that. But the direction is clear. Every pulse, burst, spectrum, polarization measurement, merger, and non-detection narrows the physical possibilities. The most extreme objects in space are becoming less distant from explanation, even while remaining far beyond direct reach. The word extreme can also hide the continuity between neutron stars and more familiar stars. A neutron star is not made from a different universe. Its material began as ordinary stellar plasma, mostly hydrogen and helium, processed through fusion, collapse, and nuclear reactions. The path is extraordinary, but the ingredients are cosmic matter following physical laws. That continuity is what makes the object understandable at all. The same gravity that rounds planets and holds galaxies together compresses the core. The same electromagnetism that shapes atoms also shapes magnetospheres and radiation. The same nuclear forces that bind atomic nuclei resist collapse in the densest layers. The same relativity that corrects GPS clocks becomes essential near the surface. Neutron stars are not separate from familiar physics. They are familiar physics forced into an unfamiliar corner. This is why they are useful. A laboratory on Earth can isolate one effect and control conditions, but it cannot create a stable object with more than a solar mass at nuclear density. A neutron star supplies the conditions naturally, though without human control. Astronomers trade control for scale. They cannot set the experiment, but they can observe many versions of it across the galaxy. Each version comes with a different set of parameters. One star is young and hot. Another is old and recycled. One has a strong dipole field. Another may hide stronger internal fields. One accretes from a companion. Another travels alone. One merges within the age of the universe. Another will rotate quietly for billions of years. The population becomes the experiment. Theoretical models then try to explain not one perfect object, but the distribution. How many magnetars should exist? How quickly do they fade? What birth conditions make them? How often do double neutron stars merge? How much mass do kilonovae eject? How many pulsars are missed because their beams never touch Earth? These questions are statistical as much as individual. Statistics do not remove the need for close case studies. The Crab pulsar, Vela, SKR 180620, SKR 1935 plus 2154, and GW 17817 all matter because detailed observations teach what broad surveys cannot. A population gives rates and ranges. A case study gives mechanisms, anomalies, and texture. Neutron star science needs both the forest and the individual sparks inside it. The most dramatic case studies often begin as exceptions. A flare too bright. A pulse too regular. A binary orbit decaying exactly as relativity predicts. A radio burst from inside the Milky Way that resembles signals from other galaxies. Exceptions are not nuisances when they are real. They are places where theory has to become more precise. Precision does not mean removing the atmosphere from the story. A star collapsing into a neutron star is still an astonishing event. A magnetar flare is still a startling release of energy. A merger still changes the chemical future of its surroundings. The point is not to make the universe less strange. The point is to let its strangeness remain attached to what can be measured. That attachment is the difference between a mystery and a myth. A myth can be complete without evidence. A scientific mystery grows from evidence that does not yet fully explain itself. Neutron stars belong to the second kind. Their reality is secure. Their details are still unfolding. The more we measure, the more specific the remaining questions become. In the end, a neutron star is a contradiction only to intuition, not to physics. It is small and massive, dark in ordinary light and bright in invisible wavelengths. Dead by fusion and active by rotation, magnetism, accretion, or collision. Distant from human travel and close to human measurement. Its existence feels improbable until the evidence is followed step by step, from massive star to collapsed core to pulse in a telescope. That step-by-step path is why the subject can sustain such a long journey. Every layer leads to another, supernovae to remnants, remnants to pulsars, pulsars to timing, timing to relativity, magnetars to flares, flares to crust physics, mergers to gravitational waves to nuclear matter to the limits of what a star can be. The object is compact, but the story expands outward. A final pass through the data might show nothing more than a faint point in X-rays and a periodic signal in radio. But behind that small entry is the collapsed core of a massive star. The pressure of nuclear matter. A magnetic field stronger than anything built on Earth. And a clock spinning in the dark. It is enough. From such traces, the most extreme stars in the universe become visible. Even the phrase city-sized should be handled with care, because the exact radius is not fixed. Different neutron stars can have different masses and perhaps slightly different radii depending on the equation of state. A 20-kilometer object is a useful mental picture, but the measurement problem remains active. The city is a scale, not a blueprint. The same care applies to magnetic strength. Magnetars are described by surface dipole fields inferred from timing, but their internal fields may be stronger and their local surface fields more complex. A single number cannot capture the geometry of a twisted magnetic star. It is a beginning, not a complete map. Instruments will keep refining those maps. A better X-ray pulse profile, a cleaner polarization measurement, a new glitch, or a flare caught from its first instant can change what is known about a single source. A single source, understood well, can then change how the whole class is modeled. That is why the watching continues long after the first discovery announcement fades. The pulse repeats, the crust cools, the nebula expands, the binary orbit shrinks, the archive grows. Neutron stars do not reveal themselves all at once, but they do leave records, and those records are still arriving. The records are imperfect, but they are cumulative. A pulse counted today can be compared with one counted decades ago. A flare caught by one spacecraft can be re-examined when another source erupts years later. The slow accumulation is part of the instrument. No observer needs to stand beside a neutron star for the star to become real in science. The evidence crosses the distance instead. One photon, one radio wave, one gravitational ripple at a time, until the object is no longer only predicted, but measured. And in that measured presence, the extreme becomes something more than a claim. It becomes a place in the universe with mass, radius, field, motion, history, and limits that can be tested. There is another practical reason these objects remain central to astronomy. They are small enough that the finite speed of light across their surfaces matters in timing models. A photon from one edge of a hotspot does not have exactly the same path as a photon from another. Rotation changes the energy through Doppler effects. Gravity bends the path. The pulse that reaches Earth is shaped by a compact geometry, where every correction is meaningful. For a normal star, surface details blur together across a large disk. For a neutron star, the surface cannot be resolved, but rotation turns geography into time. A bright region becomes a pulse. A second region becomes another feature. The shape of the waveform is a substitute for a picture, and in some ways a more precise one, because it carries information that a distant image could not easily show. The same substitution happens in radio timing. A pulsar is not imaged as a spinning globe. Its rotation is inferred from periodic arrival times. If the star has a companion, the orbit is inferred from delays. If it glitches, the interior is inferred from a sudden change in spin. Time becomes the observing surface. The clock is the image. This is why neutron stars reward long attention. A single pulse proves very little. 1,000,000 pulses can reveal a period. Years of pulses reveal spin down, position, proper motion, binary effects, and irregularities. Decades of pulses can test gravity and search for low-frequency gravitational waves. The object is compact, but its scientific value expands with the duration of the record. Magnetars ask for a different kind of attention. They may offer long periods of faint emission, then compress crucial information into a short burst. To study them well, astronomers need both monitoring and memory. The monitoring catches the event. The memory, stored in archives, tells what changed. Without the quiet before, the flare after has less meaning. A neutron star, in that sense, is never only an object at a coordinate. It is also a record in time, and the longer the record becomes, the more of the hidden star can be inferred. A final image can be simple. A radio dish sits under a cold sky, aimed at a point that no eye could distinguish from the surrounding stars. The receiver records a pulse, then another. The interval is almost the same, but not perfectly, because the star is slowing, moving, and living through its own physics. The signal crosses the galaxy and becomes a line in an archive. Elsewhere, an X-ray telescope waits for photons from a magnetar that may remain quiet for years. A gamma-ray monitor watches the whole sky for a flare that may last less than a heartbeat. A gravitational wave detector holds its mirrors still enough to listen for the final seconds of two dense remnants falling together. The instruments are different, but the question is connected. What happens when a star becomes almost as dense as an atomic nucleus and still does not disappear? What happens when a magnetic field becomes strong enough to power a star's light after fusion has ended? What happens when two such remnants collide and throw neutron-rich matter into space? The answers are partial, but they are not imaginary. They are written in signals already arriving. The next signal may be ordinary, another pulse added to a timing solution. It may be rare, a magnetar flare from across the galaxy. It may be historic, a nearby neutron-star merger with light and gravitational waves arriving together. Whatever form it takes, it will probably begin the same way so many discoveries begin now, as a small change in a stream of numbers. Noticed because someone built an instrument patient enough to wait. Beyond the atmosphere, the detectors keep watching. The neutron stars continue to turn. Magnetars hold their stressed fields in the dark between outbursts. Supernova remnants expand and fade. In the archives, pulses accumulate one rotation at a time, and somewhere inside those quiet records, the densest stars we can still call stars continue to reveal themselves by degrees.